At the heart of our vast Milky Way galaxy, an enigma resides. Hidden by an impenetrable veil of cosmic dust and countless stars lies something our eyes can never truly perceive. An object with a colossal mass of millions of suns. Its name is Sagittarius A, and it is a supermassive black hole. Yet unlike the roaring cosmic engines that fuel distant quasars and blaze in active galaxies, Sagittarius A is largely silent, almost imperceptibly quiet. But do not be misled by its calm demeanour. Beneath that tranquil surface, a tempest rages. A storm of twisted magnetic fields, sudden bursts of energy known as flares, and gravity so extreme. It warps the very fabric of space-time, pushing the boundaries of known physics. This is the epic tale of our relentless quest to understand this hidden titan, how humanity discovered it, the ingenious methods used to photograph the unseeable, and the profound lessons this black hole has imparted about our universe, and indeed about ourselves. For millennia, the true core of our galaxy remained shrouded in mystery. Even as early astronomers peered skyward, meticulously charting planets and mapping constellations with ever-improving scientific instruments, the Milky Way's centre remained stubbornly hidden. Every time their nascent telescopes turned towards the thickest, brightest part of the galactic band towards the constellation Sagittarius, they hit a wall. A wall woven from light and shadow, vast clouds of gas and dust and stars packed so tightly they bled into an indistinct glow. This dense luminous region, now known as the galactic bulge, is one of the most crowded environments in the entire Milky Way. It is a gigantic central swelling and ellipsoid of starlight composed of hundreds of billions of stars. From our vantage point on Earth, it lies precisely in the direction of the galactic centre, but piercing its depths was for centuries an almost impossible feat. When we gaze at the Milky Way with the naked eye, we perceive a faint pale band stretching across the night sky, often mistaken for a wispy cloud. This ethereal glow, however, is not mist. It's the combined light of untold billions of stars. This celestial river of light grows brightest near the galactic core. But hand in hand with that brilliance comes a profound darkness. This isn't the void between stars, it's the presence of dust. Throughout the galaxy, drifting silently in the vast spaces between stars, are colossal clouds of interstellar dust. These clouds are comprised of minuscule particles, bits of carbon, frozen gases, and rocky debris, the leftover remnants from older deceased stars slowly migrating through the cosmic expanse. Though individually tiny, spread out over unimaginable distances, these particles are incredibly effective at blocking light, especially the visible light that our eyes and early telescopes could detect. And nowhere in the sky is this dust thicker, this cosmic curtain denser, than in the direction of the galactic centre. For most of human history, our telescopes functioned like giant sophisticated eyes, gathering visible light and focusing it into images. But visible light is easily scattered or absorbed by dust. It was as if someone had draped a thick velvet curtain across the middle of the Milky Way. Astronomers looking towards Sagittarius saw only a bewildering chaos, a thick blurred mass of stars interwoven with dark streaks, like smoke smeared across a painting. The nearby stars were visible, but beyond them an impenetrable darkness. The light from the galaxy's true heart simply could not reach us. The very structure of the galactic bulge compounded the problem. Unlike the relatively flat, pancake-like disk of stars that forms the galaxy's outer arms, the bulge is a swollen spherical region. It is far thicker and denser than the outer regions, with stars packed so tightly they overlap and shine in every direction. Yet paradoxically, because there are so many of them, and because of the dense dust mixed throughout their individual light, becomes incredibly difficult to separate. The signals were there whispering secrets, but they were lost in the overwhelming static of the cosmic noise. This rendered the centre of our galaxy one of the most enigmatic regions in the entire sky. Humanity could map the outer arms chart nearby star systems, but what truly lay at the heart remained an open question. Did the galaxy even have a heart? Was it merely a loose collection of stars, or was there a true unifying centre around which everything spun? Early astronomers observing stars seemingly spread evenly in every direction from Earth mistakenly concluded that our Sun must be near the Milky Way's centre. This skewed perception, a consequence of the dust blocking their view of the actual core, painted a false picture of galactic structure. In the 18th and 19th centuries, figures like William Herschel attempted to map the galaxy's shape by counting visible stars. Their star counts showing more stars in some directions and fewer in others led them to assume the galaxy was unevenly shaped. They were unaware of the vast obscuring clouds of interstellar dust that subtly manipulated their perception, hiding the true extent and form of our stellar home. It was a profound limitation, one that would only begin to unravel with the dawn of the 20th century. The paradigm shifted with the development of new types of telescopes, instruments that transcended the limitations of visible light. Scientists made a crucial realization to peer through the cosmic fog they needed to harness forms of light that could bypass the dust with greater ease, such as infrared and radio waves. These ethereal wavelengths, invisible to our human eyes, carry information just as visible light does. But unlike visible light, they can penetrate dense dust clouds without being scattered or absorbed as much. With infrared telescopes, astronomers could finally begin to gaze into the heart of the galactic bulge, revealing stars previously hidden behind dust clouds, and slowly mapping the true contours of the centre. Radio telescopes, meanwhile, picked up entirely new kinds of signals from the galaxy's depths, waves of energy emanating from strange sources never before conceived. A pivotal moment arrived in the 1930s and 40s when radio astronomers began detecting an exceptionally strong signal originating from the constellation Sagittarius. This wasn't the signature of a normal star, nor anything familiar. It was a powerful, persistent source of radio waves pinpointed right at the Milky Way's very centre. They christened it Sagittarius A. Initially, it was just a bright anomalous spot in their radio images buried deep within the galactic bulge. But with each passing year, as instruments grew more sophisticated and scientists scrutinized the region with increasing precision, a profound realization dawned: something profoundly strange resided there. Something immensely massive, utterly invisible to conventional telescopes and powerful enough to compel stars into astonishingly rapid orbits around it. However, even with these new eyes, the dense dust and gas continued to make detailed study of the galactic centre immensely challenging. Astronomers were forced to develop ever more advanced instruments, building observatories on remote mountaintops, launching instruments on high-altitude balloons, and eventually deploying telescopes into the vacuum of space to obtain clearer, unobstructed views. The galactic bulge remained one of the most crowded, chaotic, and complex regions of the galaxy. Adding to the difficulty was the sheer speed of the stars within the bulge. They weren't leisurely drifting, they were whipping around the centre in tight, incredibly fast orbits. Tracking these breakneck motions demanded extreme precision, requiring years of meticulous observation of the same stars, collecting countless measurements to understand their intricate paths. Only then, with painstaking patience, did the cosmic patterns begin to emerge. All these factors, the dust, the stellar density, the furious motion, conspired to keep the truth hidden for the vast majority of human history. While ancient civilizations spun myths and early scientists offered educated guesses, the true centre of the Milky Way remained an obscured secret veiled by its own majestic structure, behind a glowing, swollen mass of stars and a thick interstellar fog. Only by learning to look with entirely new kinds of eyes could we begin to see it for what it truly was. The radio signal that would ultimately change everything began not in a dedicated astronomy lab, but with a young engineer named Carl Jansky, working at Bell Telephone Laboratories in New Jersey in the early 1930s. His mission was far from astrophysics. He was simply tasked with solving a practical problem for nascent long-distance radio communication. At the time, radio technology was booming and clean signals were vital, yet strange background noises and unexplained static plagued transmissions. Jansky was charged with tracing the source of this interference, To accomplish this, he constructed an odd-looking apparatus, a large rotating antenna affectionately dubbed a merry-go-round, due to its wheeled base that allowed it to sweep across different parts of the sky. It was designed to capture radio waves in the shortwave band around 20.5 ms, a frequency much lower than visible light but crucial for communication. Jansky spent months meticulously collecting data. He identified various sources of static, some from nearby thunderstorms, others from distant lightning. But one particular source of noise exhibited a remarkably regular pattern, appearing approximately once every 24 hours. Initially he suspected it was linked to the sun. However, as weeks turned into months, the timing subtly shifted, arriving roughly 4 minutes earlier each day. It was then that Jansky had his breakthrough realization this mysterious source wasn't tied to Earth's rotation relative to the sun, but rather to its rotation relative to the fixed stars. In other words, it was coming from space itself. The signal's direction pointed unmistakably towards the constellation Sagittarius, and thus the centre of the Milky Way. This accidental discovery marked the very first detection of radio waves from beyond our solar system, inadvertently birthing the entirely new field of radio astronomy. Jansky's groundbreaking discovery, born from routine engineering work, initially garnered little excitement among astronomers, who remained largely focused on optical telescopes and underestimated the profound implications of radio signals from space. Jansky himself didn't pursue space research, and Bell Labs moved on, eventually dismantling his unique antenna. Yet the seed of discovery had been planted. A few years later, a self-taught radio engineer and amateur astronomer named Grota Reber picked up where Jansky left off. Inspired by Jansky's work, Reber constructed his own parabolic radio dish, an impressive 9 meters across, in his Illinois backyard. He systematically scanned the sky for radio waves, confirming Jansky's findings and for the first time mapping the radio sky. His maps clearly showed strong radio signals emanating from the same region, Sagittarius. Through the 1940s and 1950s, more scientists entered this burgeoning field. Radio astronomy began its rapid ascent, with larger, more sensitive antennas being constructed capable of covering a wider range of frequencies. These instruments unveiled a universe that was entirely invisible to the human eye. Objects that appeared dark and empty in visible light sometimes blazed with astonishing brilliance in radio waves. The once hidden heart of the Milky Way, shielded by dust, now began to speak in a new energetic language. By the 1960s, radio telescopes had evolved into formidable tools. Scientists could now study the galaxy's structure in unprecedented detail, detecting radio signals from gas clouds, supernova remnants, and even other galaxies. But one spot remained singularly compelling: the compact, powerful radio source in the direction of Sagittarius. This signal, first noticed by Jansky decades earlier, was coming from an extraordinarily specific point, steady, strong, and located precisely at the Milky Way's core. It didn't flicker, nor did it spread across the sky. It was remarkably compact, confined to a very small area. This suggested a source that was tiny yet incredibly powerful. Even into the 1970s, the precise nature of this compact radio source remained unknown. The signal was strong yet defied easy explanation. It didn't fit the patterns of known nebulae or supernova remnants. To unlock its secrets, astronomers understood they needed to observe how stars moved around this invisible point. Such research, however, demanded immense patience and cutting-edge technology. The galactic centre is a staggering 26,000 light-years away. While stars there move at incredible speeds, their orbits are still too vast to be tracked in mere days or weeks. It required years, even decades of meticulous observation. The second half of the 20th century brought another revolutionary tool: infrared astronomy. Scientists began developing instruments capable of detecting infrared light from space. Early attempts utilized high-altitude balloons and aircraft, as Earth's atmosphere absorbs a significant portion of infrared radiation before it reaches the ground. To truly study the infrared sky, one had to ascend above the thickest atmospheric layers. A significant stride was placing infrared telescopes on mountaintops in arid, high-altitude locations like Mauna Kea in Hawaii or the Atacama Desert in Chile, where the thin, dry air allowed more infrared light to reach the instruments. From these lofty perches, astronomers began capturing the first clear images of stars and gas clouds hidden within the Milky Way centre. Even these early results were astonishing. Regions that appeared utterly dark in visible light now glowed with vibrant clusters of stars under infrared scrutiny. The heart of the galaxy was not empty but brimming with activity. What had once been a blank patch of sky now pulsed with life. Yet even ground-based infrared telescopes had their limitations. Earth's inherent heat and atmospheric interference made it difficult to obtain perfectly clear, uninterrupted data in specific infrared wavelengths. The logical next step was to venture beyond the atmosphere. In 1983, NASA launched the infrared astronomical satellite IRAS, the first telescope to map the entire sky in infrared light. Though not solely focused on the galactic centre, IRAS spectacularly revealed how much of the cosmos was hidden within dusty regions, with entire areas that seemed empty in optical images bursting to life in the infrared filled with young stars, warm dust and enigmatic heat sources. Later space telescopes, such as the Spitzer Space Telescope launched in 2003, would delve far deeper, dedicating years to scrutinizing these hidden realms. Spitzer was particularly instrumental. With its exquisitely sensitive instruments cooled to near absolute zero, it could detect faint heat signatures from across the galaxy. One of its primary targets was the Milky Way's core. Using its infrared eyes, Spitzer observed stars swirling in dizzying orbits remarkably close to a dense and visible point. This point, already identified by radio signals as Sagittarius A, was now under unprecedented infrared observation. Simultaneously, ground-based infrared telescopes continued to advance. In Chile, at the European Southern Observatory's Very Large Telescope VLT, a team led by Reinhard Genzel embarked on a multi-year project to meticulously track the motion of stars near the galactic centre. Meanwhile, in Hawaii, another pioneering team led by Andrea Ghez used the Keck Observatory to conduct parallel observations. Both teams deployed advanced infrared cameras to pierce the dust veil, precisely following the paths of individual stars. Stars so intimately bound to the black hole that they completed their orbits in just a few years. These S-stars, as they became known, were the key to unequivocally proving what lay at the Milky Way's heart. One particular S-star, known as S2 or sometimes S02, became a celestial clock moving in a long, incredibly fast elliptical orbit that brought it extraordinarily close to Sagittarius A. By meticulously observing its path over time, both research teams were able to calculate the mass of the unseen object exerting this immense gravitational pull. The result was staggering. The object possessed the mass of approximately 4 million suns, yet it was compressed into a space smaller than our entire solar system. Critically, it emitted no light like a star. The only possible explanation was a supermassive black hole. None of these groundbreaking findings would have been possible without the advent of infrared astronomy. The dust surrounding the galactic core still blocked visible light, but in the infrared, the universe's narrative became stunningly clear. Stars danced in a cosmic ballet around an invisible force. Heat glowed where the eye saw nothing, and the true hidden shape of the galaxy's mysterious heart began to emerge from the darkness. With the right observational tools, the minute movements of stars can be measured down to fractions of an arc-second. A tiny angle in the sky, yet enough to unravel dramatic cosmic stories when observed over years or even decades. In the 1990s, this painstaking work began in earnest. One of the pioneering teams was led by Reinhard Genzel, operating from the Max Planck Institute in Germany. The other was headed by Andrea Ghez at UCLA in California. Both teams utilized powerful ground-based telescopes equipped with revolutionary adaptive optic systems to peer through the obscuring dust of the galactic center. Even with infrared telescopes, the challenge was immense. Earth's turbulent atmosphere is a constant source of interference, blurring images, and causing stars to shimmer and seemingly dance randomly. To counteract this atmospheric distortion, astronomers deployed a groundbreaking technology called adaptive optics. This innovation allowed the telescopes to adjust their deformable mirrors in real time, effectively cancelling out much of the blurring caused by the air above. Near Sagittarius A, these teams discovered stars moving at truly astonishing speeds, like cosmic projectiles whipping around an invisible campfire. Some reached velocities exceeding 5,000 kilometers per second, fast enough to travel from Earth to the Moon in just over a minute. The critical breakthrough came from tracking these stars over extended periods. One star in particular, S2, shone brightly as it followed a tight, rapid orbit around a completely dark region of space. Over merely 16 years, S2 completed a full loop, a feat of precision tracking never before achieved for a star so close to the galactic centre. S2's elliptical path mirroring the orbits of planets around a star unequivocally demonstrated that it was responding to an immense gravitational force. From the precise orbit of S2 and other nearby stars, astronomers could calculate the mass of whatever was exerting this pull. The answer was staggering: over 4 million times the mass of our Sun, all packed into a region smaller than our solar system. This left only one explanation: a black hole. Not just any black hole, but a supermassive one. This represented the most direct and compelling evidence yet for such an object, confirming decades of theoretical speculation. While black holes had been suspected and theorized for decades, mostly studied indirectly through X-ray emissions from distant galaxies or computer simulations here. For the first time, scientists were witnessing real stars orbiting a truly invisible entity in real time. The evidence continued to mount with each passing year. More stars were tracked, some with longer orbits, others even closer to the centre than S2. All of them pointed to the same central invisible object. Crucially, their orbits behaved precisely as predicted by Einstein's general theory of relativity. Their paths exhibited subtle, almost imperceptible shifts in timing and direction that could not be explained by Newton's laws of gravity alone. This demonstrated that the gravitational field near Sagittarius A was not only extraordinarily strong, but it was actively warping space-time itself, just as Einstein predicted. In 2002, Andrea Gheze's team published the first complete orbit of S2. Reinhard Genzel's group followed suit in 2008 with even more precise measurements. The results from both teams working independently on opposite sides of the world were virtually identical, converging on the same undeniable conclusion: a massive, invisible object resided at the centre of our galaxy, its gravitational pull dictating the motion of nearby stars. It could be nothing else but a black hole. As technology progressed, observations became even sharper. By the 2010s, telescopes were capturing stellar positions with astonishing accuracy, down to 1,000th of an arc-second, a precision akin to measuring the width of a human hair from several kilometers away. These meticulous measurements consistently reaffirmed the initial finding: Sagittarius A was real, it warped the space around it, and it was undeniably a black hole. Yet despite all this profound understanding, we still had not seen it directly. We had observed its gravitational footprints, tracked its stellar dance partners, but the black hole itself remained unseen, a ghost of gravity. It would be some time before we found a way to look even closer to image the unseeable directly. When scientists first began to grasp the concept of black holes, they realized they weren't dealing with a single monolithic type of object. While the theoretical idea is simple, a region in space-time where gravity is so intense that nothing, not even light, can escape, the mechanisms by which these objects form, evolve and behave can vary dramatically. This is why astronomers categorize them into different classes of black holes. The one at our galaxy's heart, Sagittarius A, belongs to the largest known class, supermassive black holes. But it is far from the only kind. Understanding these other types helps illuminate just how unique and significant our galactic centre truly is. The smallest known black holes are called stellar mass black holes. These are the remnants of massive stars born from their cataclysmic demise in supernova explosions. When a star several times heavier than our Sun exhausts its nuclear fuel, it can no longer counteract the crushing force of its own gravity. Its core collapses, and if the remaining mass is sufficiently high, it transforms into a black hole. These cosmic objects are tiny on a galactic scale, perhaps only a few kilometers across, yet they contain more mass than our entire Sun. Despite their diminutive size, they can exert powerful influences on their surroundings, particularly if they siphon material from a companion star, forming a glowing accretion disk that radiates intensely in X-rays. Dozens of these stellar black holes have been identified throughout galaxies, including our own, through careful observation of their energetic emissions. A step up in mass, though much harder to detect, are intermediate mass black holes ranging from hundreds to thousands of times the Sun's mass. Their origins remain a captivating mystery. Some theories posit they could form from the merger of multiple stellar black holes within dense star clusters, while others suggest they might grow by steadily consuming gas and stars over vast timescales. Their rarity and observation makes them particularly intriguing, as intermediate black holes could represent a crucial missing link in the growth process from stellar mass to supermassive black holes. If these mid-sized objects are indeed numerous, they could be the cosmic seeds that eventually grow into the colossal giants residing at galactic centres. Then there are the true leviathans, these supermassive black holes weighing in at millions to billions of times the Sun's mass. Sagittarius A is on the lighter end of this spectrum, yet even that makes it unimaginably powerful. Unlike stellar black holes, which form from the collapse of a single star, supermassive black holes could not have originated from one sudden collapse. They must have accumulated their immense mass over cosmic time, perhaps, beginning with the direct collapse of enormous gas clouds in the early universe, or through successive mergers of smaller black holes and star clusters. Almost every large galaxy observed appears to harbour one of these giants at its core, and they play a pivotal role in shaping their host galaxy's evolution. Beyond observation, there exists a type of black hole purely in the realm of theory, primordial black holes. These would have formed not from stars but from extreme density fluctuations in the very early universe, mere moments after the Big Bang. The idea is that tiny regions of space-time could have been so incredibly dense that they collapsed directly into black holes, some no bigger than an asteroid, others potentially far larger. If they exist, they could be scattered throughout the cosmos, perhaps even silently passing through our solar system, from time to time entirely undetected. Some scientists even propose that certain unexplained cosmic phenomena, like gamma-ray bursts or dark matter signals, could be subtle clues to the existence of such ancient black holes. Another intriguing theoretical variant is the ultramassive black hole, an extension of the supermassive category, with masses exceeding 10 billion suns. A few candidates have been observed at the centres of extremely large galaxies, their sheer size prompting fundamental questions about the ultimate limits of black hole growth and the speed at which they can accumulate matter. Sagittarius A fits firmly within the supermassive category, but it possesses distinct qualities. Compared to the largest black holes in the universe, it is remarkably quiet. Many supermassive black holes are active, gorging on vast amounts of material and unleashing blazing jets of energy, visible across billions of light years. Our galactic centre, however, is currently in a low activity phase, feeding only sporadically and producing only brief faint flares in radio-infrared and X-ray wavelengths. This relative quietude makes it harder to study in some respects, as it lacks the bright, unmistakable emissions of active galactic nuclei. Yet paradoxically, it also transforms Sagittarius A into an ideal cosmic laboratory for studying the black hole itself, free from the overwhelming chaos of extreme feeding events. By comparing Sagittarius A to its more ferocious cousins, scientists gain invaluable perspective on its unique role in our galaxy. While stellar black holes are common, their influence is localized, affecting only their immediate cosmic neighborhoods. Intermediate black holes, if confirmed in abundance, could bridge the evolutionary gap but remain elusive. Supermassive black holes, however, shape entire galaxies, binding them with their immense gravity. and influencing the movement of stars and gas far beyond their event horizons. And should primordial black holes exist, they could offer profound insights into the universe's earliest moments, though detecting them would be an infinitely greater challenge than tracking the colossal object at our Milky Way's core. All these diverse types, from the smallest stellar remnants to the most colossal supermassive titans, share one unifying, terrifying trait: their gravity is absolute. Once anything crosses their event horizon, it is irrevocably gone from the observable universe. Yet their differences paint a vivid picture of the immense cosmic diversity within the very concept of a black hole. This diversity is precisely why astronomers do not study Sagittarius A in isolation, but instead place it within the broader context of black hole research, allowing us to discern what is typical and what is truly unusual about our own galactic centre. The unusual name Sagittarius A itself holds a story of discovery. From Earth's embedded position within the Milky Way, we lack an overhead view of our galaxy. So astronomers rely on constellations as celestial signposts to denote regions of the sky. When they speak of something being in Sagittarius, it indicates its apparent location within the constellation's boundaries, not a direct affiliation with the constellation's stars. As astronomers investigated the Sagittarius region with their new radio telescopes, they identified a cluster of distinct radio sources, all located near the galaxy's centre. To systematically track these signals, a naming convention was essential. In the early 1970s, astronomers Bruce Balick and Robert Brown, utilising high-resolution radio imaging, meticulously focused on a compact point at the very heart of this central cluster. They designated the entire group Sagittarius A, following the established naming tradition in radio astronomy, where A denoted the first major radio source discovered in a given constellation. Subsequent discoveries in the same region would be labelled Sagittarius B, Sagittarius C, and so forth. Within this Sagittarius A complex, Balick and Brown pinpointed what appeared to be, with the technology of the time, the central engine, perhaps the core of the entire Milky Way. It was then that they bestowed upon it its distinctive name, Sagittarius A, written with an asterisk. At the time, Balick and Brown borrowed a coding style from atomic physics, where an asterisk occasionally signified an excited state, a version of an atom or particle with elevated energy. While not a formal astronomical naming rule, it felt appropriate. This particular Sagittarius A source was demonstrably more intense, more concentrated, and far more mysterious than the surrounding Sagittarius A components. The asterisk was their subtle yet powerful way of highlighting its unique energetic nature. The name stuck. In the decades that followed, as astronomers worldwide increasingly focused on this strange point at the Milky Way's centre, Sagittarius A became the standard nomenclature, appearing in countless scientific papers, telescope logs, and research reports. Even as technology advanced and scientists grew increasingly confident that this object was a black hole, millions of times more massive than the Sun, the name endured. In a subtle twist of cosmic irony, the asterisk, pronounced aloud as star, sits at the end of the name for an object that is fundamentally not a star. Sagittarius A does not emit its own light in the conventional sense. Instead, it pulls light inward, bends space-time, and ultimately swallows anything that ventures too close. Yet the name with its curious asterisk assigns this invisible behemoth a definitive place on the cosmic map. Astronomy as a discipline is replete with such names. Some, like Betelgeuse or Vega, echo ancient languages and mythologies. Others, like M31 or NGC 2392, are catalogue numbers, practical codes assigned by researchers striving to list thousands of celestial objects without resorting to poetic titles. When scientists unveil something new, especially something beyond the grasp of the naked eye, they often fall back on a blend of tradition, convenience, and a touch of creative flair. Radio sources, for instance, are typically named by their location and order of discovery. Pulsars, the rapidly spinning neutron stars that emit regular radio pulses, are often labelled with their precise coordinates, like PSR, Nolstensen Pludios 21. Galaxies and catalogues receive numerical designations, Messier 87, NGC, for 8, and so on. Sometimes the names are beautiful, sometimes purely functional, but in every instance they serve to help scientists track and study their discoveries. In the unique case of Sagittarius A, the name does more than merely mark a spot in the sky. It is a simple name, yet that single tiny asterisk carries the immense weight and profound mystery of an entire galaxy's heart. The question that echoes across astrophysics is profound. Why does almost every galaxy, regardless of its size or shape, appear to harbour a giant black hole at its core? These same massive gravitational anchors reside at the heart of majestic spirals, grand ellipticals, and even many irregular galaxies. Some are far larger than Sagittarius A, others considerably smaller, but the consistent pattern is undeniable. This seems to be a fundamental rule of the universe. The first hints of this cosmic universality emerge from galaxies exhibiting unusually bright central regions, active galactic nuclei AGN. These AGNs emitted colossal amounts of radiation, far exceeding what any ordinary star cluster could produce. The most compelling explanation was the presence of a supermassive black hole actively feeding on gas and dust, releasing torrents of energy as the material spiraled inexorably inward. The same logic applied to quasars, those brilliant beacons observed billions of light years away, now understood to be powered by black holes weighing millions or even billions of times the mass of our Sun. Once astronomers possessed the necessary tools, they systematically began searching for signs of these central giants in more ordinary, less active galaxies. Time and again the evidence mounted, proving their existence even in galaxies that appeared quiet and dim at their centres. In some cases the black hole was dormant, not actively consuming much material, but its immense gravitational pull was still measurable through the precise motion of nearby stars and gas clouds. It soon became incredibly difficult to find a large galaxy that didn't have one. The central question then shifted from, does our galaxy have a supermassive black hole, to why does every galaxy seem to have one? The simplest explanation would be that these colossal black holes formed in tandem with their host galaxies, perhaps as an intrinsic part of the galaxy formation process itself. One theory suggests that in the very early universe, vast clouds of gas collapsed not into stars but directly into massive black holes, which then steadily grew over billions of years by devouring surrounding matter and merging with other black holes. Another possibility posits that the universe's first stars, gargantuan entities, far larger than any existing today, lived short, violent lives and collapsed into massive seeds, which subsequently blossomed into supermassive black holes. A crucial piece of this intricate puzzle is the uncanny link between the mass of a galaxy's central black hole and the mass of its stellar bulge, the dense central region of stars. This surprising relationship holds true with remarkable precision even across galaxies of vastly different sizes. This strongly suggests that black holes and galaxies engage in a profound cosmic dance, mutually influencing each other's growth and evolution. If the central black hole experiences an aggressive feeding phase, it can unleash powerful winds and jets that expel gas away from the core, effectively slowing down star formation throughout the galaxy. Conversely, if the galaxy forms more stars, the increased stellar density and stellar winds might eventually funnel more material towards the centre, providing fresh fuel for the black hole. This two-way symbiotic relationship hints at a deep coevolutionary connection, though the precise mechanisms remain a subject of intense scientific debate. The timeline of their formation also holds significant mysteries. Astronomers have observed quasars powered by billion solar mass black holes when the universe was less than 1 billion years old. This implies that these cosmic monsters formed with astonishing rapidity, far faster than many current models would predict. To achieve such colossal sizes in such a short span, something extraordinary must have occurred. Perhaps an early phase of incredibly rapid matter collapse, or a series of frequent mergers between smaller black holes. Sagittarius A is by supermassive standards relatively small. For example, the black hole in the galaxy M87, famously imaged by the Event Horizon Telescope, weighs in at several billion solar masses. Yet despite this disparity in scale, Sagittarius A fits perfectly into the same cosmic pattern. Its very presence confirms that even a relatively modest spiral galaxy like ours still harbours one of these colossal objects at its core. Some researchers have even pondered whether it's truly possible for a galaxy to exist without a supermassive black hole. A few candidate galaxies small and faint have been identified where no central black hole has been detected. However, the limitations of current technology mean we might simply be missing them. These galaxies could harbour black holes so small or so inactive that their effects are currently beyond our observational capabilities. The deeper we probe, the more it seems these central giants are fundamental to the life story of galaxies. They may act as cosmic regulators, controlling the flow of gas, the rate of star formation, and even influencing the overall shape and structure of their host galaxies. In some ways, they could be seen as the engines driving the large-scale structure of the universe. In others, more like silent governors influencing events, without always overtly revealing their presence. The fact that we don't fully comprehend their initial appearance means the story of galaxy and black hole formation is still incomplete. Were they born together side by side in the first cosmic dawn, or did the black holes emerge later carved from the first generation of stars? The evidence currently points in several directions simultaneously. By meticulously observing Sagittarius A in detail, we can test theories about black hole growth, galaxy evolution, and the strange, delicate balance that appears to exist between a galaxy's countless stars and its hidden supermassive heart. Every insight gained here might illuminate the similar structures in far more distant galaxies, whose light has travelled billions of years to reach our telescopes. Even after decades of dedicated study, the supermassive puzzle remains far from solved. We now comprehend the immense scale of the mystery, and in itself that is a profound form of progress. Yet each new discovery about these cosmic giants invariably raises new questions about their origins, and why the universe seems to insist on placing one in almost every galaxy it creates. If Sagittarius A were to magically replace our Sun in the solar system, its event horizon would immediately engulf Mercury, Venus, Earth, and Mars. We wouldn't even have time to register the change before our world was plunged into eternal darkness. Yet in the terrifying realm of the universe's largest black holes, Sagittarius A is far from the king of the mountain. It's not even a contender. Consider the black hole at the centre of the galaxy, M87. The very one famously captured in the Event Horizon Telescope's groundbreaking image of 2019. This black hole boasts a mass of approximately 6.5 billion solar masses, over 1/600 times more massive than Sagittarius A. It is so immense that our entire solar system, including the vast Oort cloud, would comfortably fit within its event horizon. Despite its gargantuan scale, M87's black hole isn't even in the running for the absolute largest ever discovered, showcasing the truly wild-sized spectrum these objects can attain. Then there is Holm 15A, a central black hole residing in a galaxy cluster over 700 million light-years away. This titan has been estimated to weigh an astounding 20 billion solar masses. It anchors the core of what is itself the largest galaxy ever found, with a sprawling, diffuse halo of stars. If Sagittarius A were somehow swapped with Holm 15A, the gravitational upheaval would fundamentally reshape the entire Milky Way. The orbits of countless stars would shift dramatically, and our galactic central bulge would become far denser and brighter due to the intense, overwhelming gravitational pull. And then there is TON 618. This true monster represents one of the largest known black holes in the entire universe, making Sagittarius A appear like a mere pebble beside a towering skyscraper. Estimates place TON 618's mass at an incomprehensible 40 billion times that of our Sun. To grasp this scale, you would need to line up over 10,000 black holes the size of Sagittarius A just to match its mass. TON 618's event horizon is so vast that light would take approximately a week to traverse it, compared to a mere 24 seconds for Sagittarius A. The scale truly defies everyday comprehension. What's fascinating is that even though these behemoth black holes are so much larger, they aren't necessarily dramatically more dangerous in their immediate environments. A black hole's gravitational pull only becomes overwhelming when one is incredibly close to it. Beyond that critical zone, its gravitational influence is precisely like any other object of the same mass. In other words, if our Sun were magically replaced by a black hole of equal mass, Earth's orbit would remain entirely unchanged. It would simply be very, very dark and cold. The same principle applies on the scale of galaxies. A larger black hole doesn't inherently mean it's perpetually devouring stars by the millions each day. It simply possesses the potential to do so if something strays too close. The fundamental difference lies in how these black holes grow, and crucially how active they become. Sagittarius A is comparatively quiet, gently feeding on small amounts of gas and dust, producing only weak flares of X-rays and radio waves occasionally. In stark contrast, something like TON 618 is an active quasar, meaning it is relentlessly devouring matter at a phenomenal rate. As material spirals towards it, it forms a blindingly bright accretion disk, so luminous it can outshine entire galaxies. This intense feeding frenzy not only powers its astonishing brightness, but also allows it to continue growing even larger over cosmic timescales. Astronomers theorize that Sagittarius A may have once been far more active in the distant past. Evidence suggests that millions of years ago, it could have flared brightly enough to send powerful radiation sweeping across the Milky Way. Some remnants of that ancient activity might still be discernible today, such as the mysterious Fermi bubbles, colossal lobes of gamma-ray emission extending above and below the galactic plane. If this hypothesis is correct, then Sagittarius A might have been more akin to a small-scale quasar in its youth, before settling into its current more subdued phase. When comparing these cosmic giants, scientists also scrutinize their spin rates. The rotation of a black hole can profoundly influence how it pulls in matter, how it shapes powerful jets of particles, and how it warps the surrounding space-time. Sagittarius A's spin rate is still being meticulously measured, but some of the larger black holes, like M87s, are believed to spin close to the maximum possible rate allowed by the laws of physics. This rapid spin can act like a cosmic blender, whipping up surrounding material and launching it into space at nearly the speed of light. TON 618's spin is less certain, but given its immense size and activity, it almost certainly possesses a colossal reservoir of rotational energy. Sagittarius A likely began as a smaller black hole gradually accreting gas dust and unfortunate stars over eons. But TON 618 and Holm 15A must have had a colossal head start. Some hypothesize they formed from the direct collapse of enormous primordial gas clouds. Others suggest they grew through multiple violent mergers with other black holes during colossal galaxy collisions. Sagittarius A itself has probably gained some of its mass through such mergers. The Milky Way has a long history of colliding with smaller galaxies, each potentially bringing its own central black hole. Over billions of years, these smaller central objects would have spiraled toward the core, merging with Sagittarius A and adding to its mass. While it's improbable our galaxy will ever host a black hole as gargantuan as TON 618, future mergers, including the inevitable collision with the Andromeda Galaxy, will undoubtedly provide Sagittarius A with a significant growth spurt. In a few billion years, our central black hole could easily become several times larger than it is today. These comparisons also serve as a stark reminder of the sheer diversity of black hole environments in the universe. Sagittarius A resides in a fairly calm spiral galaxy, surrounded by a mixture of old and new stars and moderate amounts of gas. TON 618 conversely sits in a far more active setting, its quasar activity lighting up the cosmos. M87's black hole lies in a giant elliptical galaxy at the heart of a dense cluster, a region where galaxies frequently interact and violently collide. The sheer size of a black hole is only one chapter in its story. The cosmic neighborhood it inhabits plays an enormous role in shaping its behavior and destiny. These surprisingly quiet giant black holes by their very nature do not slow down with age. If matter falls towards them, they will inexorably devour it. The difference in their activity boils down to the amount of fuel readily available at any given moment. Sagittarius A is surrounded by relatively little gas and dust compared to the central black holes of active galaxies. The sparse material that does drift near tends to be scattered or heated in such a way that much of it never makes it all the way to the event horizon. Instead, it orbits for a while, sheds some energy, and then is often expelled back into space by powerful winds and turbulence. Only a minuscule trickle of matter actually reaches the point of no return. Because this feeding rate is so low, Sagittarius A is incredibly faint, at least in black hole terms. Its emissions across radio, infrared, and X-ray wavelengths are minimal compared to its more voracious cousins. Quasars can be thousands, even millions of times brighter. If our black hole were to suddenly begin consuming matter at the rate of an active quasar, the night sky would be transformed forever. A brilliant blazing source would appear at the centre of the Milky Way, visible even in daylight, easily outshining most of the stars. This scenario is both fascinating and a little unsettling, as it would dramatically alter the appearance of our home galaxy. This subdued state is precisely one of the reasons Sagittarius A was so notoriously difficult to discover in the first place. Had it been as fiercely active as the black holes and quasars, its presence would likely have been detected far earlier. The initial X-ray and radio detections of the galactic centre were so faint that scientists required years of patient, dedicated observation to be certain of what they were witnessing. Even at 26,000 light-years distant, an actively feeding black hole would be an overwhelming beacon across the cosmos. The calm demeanour of Sagittarius A offers astronomers crucial insights into its surroundings. It suggests that the central region of our galaxy has experienced a relatively peaceful phase for millions of years. Other galaxies show clear evidence of violent outbursts from their central black holes. Vast jets stretching thousands of light-years, colossal bubbles of radio emission expanding into intergalactic space, and shock waves heating surrounding gas to extreme temperatures. Our own galaxy, by contrast, shows only subtle hints of past activity, such as the enigmatic Fermi bubbles, which might be echoes of a more energetic era. If this interpretation is correct, then our black hole is simply between meals right now, enjoying a period of cosmic quietude. Some scientists believe this stillness might only be temporary. There are still vast clouds of gas and intricate streams of stars in the central region, and the relentless dance of orbital mechanics ensures that from time to time something will inevitably wander too close. When that happens, a sudden dramatic flare-up of activity could occur. Indeed, astronomers have observed brief outbursts from Sagittarius A in recent decades. Sudden transient increases in X-ray and infrared brightness, often lasting only hours before fading once more. These fleeting events could be caused by small amounts of material falling in, producing a momentary flicker before the profound calm returns. It's as if the giant occasionally stirs in its sleep a restless murmur from a cosmic leviathan. Many of the most active quasars host black holes billions of times more massive than the Sun. Their sheer size allows them to draw in far greater quantities of matter and radiate commensurately more energy. This size difference likely explains in part their higher level of activity, as a smaller gravitational influence over Sagittarius A's immediate surroundings might limit the amount of material it can capture. Yet size isn't the sole determinant. There are known black holes with masses similar to or even smaller than Sagittarius A that exhibit far greater activity. This reinforces the idea that the primary distinguishing factor is the environment. If the Milky Way's central region possessed a denser, more continuous supply of gas and dust, the story might be very different. In that alternate reality, Sagittarius A could blaze like the core of an active galaxy, profoundly influencing star formation across the Milky Way and dramatically reshaping the structure of our galactic home. The current quietude offers a unique scientific advantage. When astronomers point telescopes towards Sagittarius A, they can discern intricate details in the surrounding stars and gas that would be completely obscured if the black hole were more active. This has enabled incredibly precise tracking of stars in its vicinity, yielding invaluable data on stellar orbits and gravitational interactions. The calm environment also means that even subtle changes in brightness can be studied in exquisite detail, offering profound insights into the precise mechanisms of how black holes feed, even at exceptionally low rates. Even in this subdued state, Sagittarius A emits detectable radio waves and produces occasional X-ray and infrared flares, which, while faint compared to quasars, are still significant for understanding its dynamic behaviour. These flares provide brief, tantalising glimpses of the complex processes occurring near the event horizon, illustrating how magnetic fields, turbulence, and superheated plasma interact under the most extreme conditions imaginable. There is a certain profound mystery in observing something so unimaginably massive, so fundamentally extreme in its nature, and yet so remarkably restrained. It feels almost unnatural, a cosmic predator choosing not to hunt. Perhaps this is merely a lull in its immensely long history. Galaxies live for billions of years, and over such vast timescales, the feeding habits of their central black holes can shift dramatically. 1 million years from now, or 10 million, Sagittarius A might still be quiet. But perhaps in 25 million years it will be in the midst of a violent feeding event altering the appearance and behaviour of our entire galaxy. There's even the possibility that it could suddenly consume an unusually large object like a dense star cluster, or a wandering intermediate mass black hole releasing energy on a scale far beyond what we witness today. In cosmic terms, black holes are incredibly patient. They don't require constant feeding and can endure long stretches without dramatic events. But when the right conditions coalesce, they can shift into a mode of intense activity almost instantaneously. Next-generation instruments like the Event Horizon Telescope, advanced space-based X-ray observatories, and sensitive infrared telescopes are all meticulously monitoring the black hole's behaviour. Subtle fluctuations in brightness, seemingly insignificant, can offer crucial clues about material moving inward. Even though a major outburst could be far in the future, the processes leading up to it might be detectable years or even centuries in advance. There is also a growing interest in uncovering historical traces of its past activity through other means. Studying the precise orbits and chemical composition of stars near the galactic centre might reveal lingering disturbances from ancient energetic events. Mapping the intricate gas structures in the central regions can also expose patterns shaped by older, powerful outflows. These are like the growth rings in a tree trunk, preserving a record of the black hole's past actions. Should Sagittarius A indeed enter another active phase, it would present a rare, unparalleled opportunity to study a supermassive black hole's transformation in real time. Most of the quasars we observe are so distant that their light reaches us from billions of years ago. To witness such a phenomenon within our own galaxy would grant scientists an unmatched understanding of the intricate mechanics of black hole, feeding, and feedback. It would also serve as a powerful reminder that the Milky Way, though seemingly stable, is still a dynamic and continually evolving system. The expectation of a blazing, furious ring of matter around a black hole, an accretion disk, is almost a given in astrophysics. These disks are colossal, swirling structures of gas dust, and sometimes even stars caught in a slow, inexorable spiral towards the event horizon. As this material falls inward, friction and compression heat it to unimaginable temperatures, causing it to radiate with the brightness of entire galaxies. This is precisely why distant quasars can utterly outshine everything around them visible from billions of light years away. But when astronomers gazed towards Sagittarius A, they found no such blazing, unmistakable signature. Instead, they detected something faint, so faint that for decades its very existence as a true accretion disk remained uncertain. Initially, this absence baffled scientists. After all, the central black hole of our galaxy was surrounded by countless stars, vast clouds of gas and intricate dust lanes that twisted like dark cosmic rivers through the galactic core. There seemed to be an abundant supply of raw material for the black hole to consume. The answer, as it turns out, lies not just in the black hole itself, but in the delicate, often inefficient balance of its immediate environment. One of the earliest hints came from radio and X-ray observations, which revealed that while material was indeed moving towards the black hole, most of it never made it all the way in. Instead, much of the gas appeared to slow heat up, and then be blown outward before ever crossing the event horizon. This led researchers to propose that Sagittarius A might be surrounded by what is termed a radiatively inefficient accretion flow. In simpler terms, the material spiralling towards the black hole isn't radiating much light, because it's not dense or compact enough, and a significant portion of it escapes before the final plunge. Imagine attempting to build a roaring bonfire, but instead of tightly stacking the logs, you scatter them loosely in a wide circle. The heat would still be present, but it would dissipate into the air without creating the bright, intense flame you expect. This analogy roughly describes what occurs around Sagittarius A. The gas spiralling inward is too spread out and too dynamically unstable to coalesce into a tightly packed brilliant disk. Instead, much of it swirls in a diffuse manner and is eventually ejected back into space by powerful magnetic fields and turbulent flows. There's also the fundamental question of supply. For an accretion disk to blaze with the astonishing brightness seen in active black holes, it requires a constant and massive influx of matter. In galaxies hosting quasars, this fuel often originates from intense bursts of star formation near the core, which drive vast quantities of gas towards the centre. The Milky Way, however, is relatively calm and quiescent at this stage in its life. While numerous stars orbit incredibly close to Sagittarius, some even swinging within a cosmic hair's breadth, there is no massive sustained influx of gas. In fact, some studies suggest that Sagittarius A might be in a prolonged fasting period, consuming only a minuscule trickle of matter compared to its energetic past. Evidence from faint X-ray echoes bouncing off nearby gas clouds hints that just a few hundred years ago, our black hole may have been hundreds of thousands of times brighter. If true, this implies that the ghostly accretion disk we observe today might be a slowly dissipating remnant, gradually fading in the absence of a fresh, abundant supply of material. The quest for this missing disk took on new urgency when the Event Horizon Telescope EHT turned its collective gaze towards Sagittarius A. The EHT, a global network of radio telescopes working in unison as a planet-sized observatory, was able to resolve the faint halo of emission directly surrounding the black hole. What they observed was not a flat, intensely bright disk, akin to the one imaged around M87's black hole, but rather a more irregular, patchy and diffuse structure. This finding strongly reinforced the notion that Sagittarius A's accretion flow is thin, hot and chaotic, producing significantly less radiation than one might instinctively expect. However, this doesn't diminish the importance of this faint accretion flow. Even a weak emission can provide crucial clues about the behaviour of matter in the extreme gravitational environment. The subtle radiation we detect allows scientists to measure the temperature, density and motion of the gas. These measurements indicate that the plasma near Sagittarius A is incredibly hot, tens of millions of degrees, yet it remains too tenuous, too spread out to produce the blinding light of a more active system. Another piece of the puzzle comes from the orbits of the S-stars, which pass close enough to Sagittarius A to potentially shed material into its gravitational embrace, yet the accretion disk remains stubbornly faint. This has led to speculation that the black hole might be highly selective about what it consumes. Powerful magnetic fields and turbulent flows within the surrounding plasma could be acting as a cosmic shield, deflecting much of the infalling gas before it can reach the inner disk. Still, the mystery persists. Was this ghostly disk always this way, or is its current state the result of a recent dramatic drop in feeding? Will it flare back to life if a large cloud of gas or a hapless star ventures too close? In 2014, the gas cloud G2 passed by with little more than a whisper of activity. This may have been because G2 was a star cloaked in dust rather than a free-floating gas cloud, which would explain why so little material actually ended up in the disk. What is certain is that the missing accretion disk isn't truly missing. It's simply faint fragmented and severely underfed. For now, we reside alongside a sleeping giant, its immense hunger surprisingly subdued. Every so often, the subtle, dim glow surrounding Sagittarius A is abruptly punctuated by a sudden burst of light seemingly from nowhere. These flashes, or flares, as astronomers call them, appear without warning. One moment, the region near the black hole is quiet and subdued. The next, it's as if someone has momentarily turned up the cosmic brightness knob before letting it fade again. These flares can be remarkably dramatic. Sometimes the brightness can increase dozens of times above its usual level, only to return to normal within a couple of hours. They don't adhere to a fixed schedule, nor are they tied to any obvious predictable phenomenon we can foresee. And because Sagittarius A is hidden behind thick clouds of gas and dust, the suddenness and unpredictability of these events make them all the more intriguing. When a flare occurs, scientists drop everything. They scramble to point every available telescope at it, desperate to gather every scrap of information before it dissipates. The first time astronomers noticed these flares, they were astonished by both their intensity and their speed. The rapid timing suggested that these bursts were originating from an extremely compact region very close to the event horizon, no larger than the distance light could travel in a few minutes. This was a powerful clue that something intimately connected to the black hole's immediate surroundings was responsible. But what exactly? One leading explanation posits that these flares are caused by clumps of gas falling inward. Under normal conditions, the matter around Sagittarius A is too thin and sparse to produce significant light. However, occasionally a denser pocket of material, perhaps from a nearby star shedding its outer layers, or a cloud of dust drifting too close, finds itself caught in the black hole's relentless gravitational grip. As it spirals inward, this gas heats up to millions of degrees, releasing a violent burst of energy before finally vanishing into the black hole. This event would create a sudden observable flare. Another compelling possibility involves magnetic fields. Black holes can twist and tangle magnetic field lines in their vicinity, storing colossal amounts of energy. If these magnetic fields suddenly reconnect, a process similar to what drives solar flares on our own sun, they could unleash a rapid burst of radiation. In this view, the flare isn't merely a byproduct of infalling matter, but a direct release of pent-up magnetic energy. This mechanism could explain why some flares appear without any discernible sign of new material being swallowed. A third, though less frequent idea suggests that flares could be triggered by stars or even smaller black holes passing perilously close to Sagittarius A. In such encounters, intense tidal forces could rip apart chunks of material, sending them spiraling into the black hole and generating a momentary intense flash. While less likely to be a frequent occurrence, the galactic centre is a crowded place, so it cannot be entirely ruled out. Astronomers cannot simply schedule an observation and expect a flare to appear. It's a cosmic waiting game. Teams sometimes monitor Sagittarius A for weeks at a time, patiently hoping to catch even a single brightening event. And when they do, they must react with lightning speed, coordinating observations with telescopes on the ground and in space to record the flare across as many wavelengths of light as possible, from radio waves to X-rays. The ultimate goal is to meticulously piece together a complete picture of what transpires during these brief violent episodes. Interestingly, these flares tend to occur more frequently in X-ray and infrared light than in visible light. This observation aligns with the idea that they are caused by superheated material extremely close to the black hole. As such, high-energy environments naturally emit more in these parts of the electromagnetic spectrum. But even with this knowledge, there's no simple, consistent pattern. Some flares are stronger in X-rays, others in infrared. Some last only a few minutes, while others linger for hours. This variety suggests that more than one process might be at work. A particularly famous flare erupted in 2019 when Sagittarius A became brighter than ever recorded, more than twice its previous maximum luminosity. The intensity of this event shocked scientists, and for a brief moment they speculated whether something catastrophic had occurred, like a star being violently torn apart. However, follow-up observations suggested it was likely a massive clump of gas falling in. perhaps related to the enigmatic G2 cloud which had been drifting near the black hole for years by this point. This event dramatically showcased just how active Sagittarius A can be when it stirs from its usual slumber. If such bursts can happen today in its relatively quiet state, what might they have looked like in the past when the black hole was hypothesized to be far more active? Evidence from X-ray echoes detected in nearby gas clouds suggests that merely a few hundred years ago, Sagittarius A may have been hundreds of thousands of times more luminous than it is now. In that historical context, today's flares might be merely small-scale reminders of a much wilder, more energetic past. For now, these bursts are brief and isolated. But if the black hole's surrounding environment changes, it could begin to feed much more vigorously. The occasional flare might be the cosmic equivalent of a stomach growl before a true feast begins. Scientists are hopeful that by studying more flares in meticulous detail, they can pinpoint their precise causes and unravel the intricate physics at play. The coming years promise major advancements in this field. Instruments like the Enhanced Event Horizon Telescope are now being used to directly observe Sagittarius A. Combined with sophisticated space-based X-ray and infrared telescopes, these observations could finally allow astronomers to witness a flare as it forms, track its evolution in real time, and definitively link it to specific physical processes. This ongoing quest to understand the unpredictable flashes from Sagittarius A is a testament to humanity's tireless pursuit of knowledge, shining a light, however fleeting, into the darkest heart of our galaxy, close to the edge of Sagittarius. The fundamental rules of the universe begin to feel less like constants and more like shifting, unpredictable patterns. Here, gravity, while still paramount, is not the only dominant force. Invisible but incredibly powerful magnetic fields twist and writhe like living entities, threading through the surrounding space-time, guiding the flow of charged particles, plasma, and sometimes, perhaps, choking it off entirely. For a long time, astronomers considered magnetism near a black hole to be merely a byproduct, a background feature of the swirling gas. But it's becoming increasingly clear that these tangled fields might be at the very heart of the black hole's enigmatic behavior. The idea of magnetic fields near a black hole might sound almost contradictory. After all, a black hole swallows everything that comes too close. How could anything, let alone a structure as seemingly delicate as a magnetic field, survive there? The key insight is that the black hole itself isn't generating these fields in the same way Earth's molten core produces our planet's magnetic field. Instead, these powerful fields originate from the plasma surrounding the black hole. As this superheated gas moves and swirls, it drags its own embedded magnetic field lines with it, stretching and twisting them into extraordinarily complex knots and loops. Sagittarius A's magnetic fields are not neat, stable loops like those around our planet. They're chaotic, constantly shifting and evolving as the gas around them flows, collides and heats up to millions of degrees. The EHT's polarized light data has given astronomers their first genuine glimpse of these magnetic structures, revealing spiraling patterns in the faint glow around the black hole. These patterns conclusively tell us that the fields are strong enough to actively shape the motion of matter, not just passively drift through it. In a profound cosmic tug-of-war, magnetism is actively competing with gravity here. Gravity relentlessly pulls everything inward, dragging it towards the inescapable event horizon. But magnetic fields can push back, especially when they become tightly wound and compressed. They can act like invisible barriers, holding material in place or redirecting it along specific paths. This could be a crucial part of why Sagittarius A remains so quiet. If the magnetic fields are organized in a particular way, they might effectively prevent gas from plunging in all at once. Instead, the material trickles in, slowly producing only weak emission. Yet these same powerful magnetic fields can also store colossal amounts of energy. When they suddenly snap or realign, a process known as magnetic reconnection, they can unleash rapid, intense bursts of radiation. A sudden reconnection event near the event horizon could accelerate particles to extreme speeds, causing them to emit X-rays and infrared light in short, sharp flashes. Precisely the flares we observe. The flare then dissipates as the stored energy is released, leaving the black hole dim again until the next event. There's also a deep mystery surrounding the three-dimensional arrangement of these magnetic fields. Some models propose they form large-scale loops extending far from the black hole, threading through the surrounding accretion flow. Others suggest a much more tangled, chaotic mess, where field lines are constantly breaking and reforming. Observations so far hint at some degree of order very close to the black hole, but increasing chaos farther out. This complex interplay could mean that Sagittarius A's environment is in a delicate balance, stable enough to prevent constant eruptions, yet unstable enough to produce occasional bursts of activity. In other black hole systems, incredibly strong magnetic fields can launch powerful collimated jets, beams of plasma shooting out at near light speed. Sagittarius A doesn't exhibit obvious large-scale jets, but there are tantalizing hints of smaller, weaker outflows. If magnetism is indeed involved, these outflows might act as a kind of cosmic pressure valve, releasing energy and gas that would otherwise feed the black hole more directly. This could be yet another reason it remains so faint most of the time. Near the event horizon, conditions are so extreme that the familiar rules for how plasma behaves begin to break down. Magnetic fields can influence particles in ways we can't yet fully model, especially when relativistic effects, the effects of moving at speeds close to light, become paramount. Charged particles spiraling along field lines near light speed produce polarized radiation. By meticulously studying that polarization, astronomers can decode the field's precise shape and immense strength. The patterns within this light are some of the few direct clues we possess about what truly transpires in a region we can never directly visit. The magnetism near Sagittarius A is part of a larger, profound story about the intricate interplay of forces in one of the universe's most extreme environments. Gravity may dominate the overall structure, but magnetism adds a crucial layer of complexity that dramatically alters how the black hole feeds flares and interacts with its surroundings. It's an invisible, dynamic architecture shaping a cosmic environment just beyond the point of no return. The more we understand about these twisting, fiery fields, the closer we get to unraveling the hidden engines that power black holes across the vast universe. The Schwarzschild radius is perhaps one of the most fundamental ways to describe a black hole. It defines the size of the event horizon, that point of no return. If you cross this invisible threshold, you are for all practical purposes forever gone from the observable universe. The term honours the German physicist Karl Schwarzschild, who in 1916 was the first to find a mathematical solution to Einstein's then new theory of general relativity that accurately described such an object. His elegant equations reveal that if you compress enough mass into a sufficiently small space, the gravitational pull becomes absolute at a certain radius. That radius depends solely on the object's mass. For black holes, it is virtually all that's left to define their size. For Sagittarius A, with a mass of approximately 854, testen of gern 36 Kilixnen, about 4 million solar masses, plugging that into the Schwarzschild formula, yields a radius of roughly 12 million kilometers, or about 7.4 million miles. That sounds immense, and in human terms it is, but in the cosmic theatre it's surprisingly compact. Just over 17 times the diameter of our Sun, all compressed into an invisible sphere at the very heart of the Milky Way. Everything inside that sphere is irrevocably cut off from the rest of the universe. The black hole itself is not a physical solid ball. The event horizon is not a tangible surface you could touch. It is purely the threshold where space-time itself bends so steeply inward that no outward path, not even for light, exists. From a safe distance, the Schwarzschild radius is a purely mathematical construct. One could orbit near it, circle around it, or even hover just outside it if one possessed some impossible means to counteract the crushing gravity. But venture closer, and the cosmic landscape fundamentally shifts. Space-time itself is falling inward, pulled faster and faster as it approaches the event horizon. The closer you are, the more extreme time dilation becomes. From your own perspective, everything would seem perfectly normal. From the outside, however, you would appear to slow down, your light shifting to red, fading, and eventually disappearing entirely before you ever seem to cross the line. The Schwarzschild radius marks the point where the inward pull effectively becomes infinite from the outside universe's perspective. Sagittarius A's Schwarzschild radius has been the focus of intense scientific scrutiny in recent years, especially with the groundbreaking work of the Event Horizon Telescope EHT. The EHT image of Sagittarius A depicts a glowing ring of radio light surrounding a dark central region. That dark centre was not the black hole itself, but its shadow, a slightly larger silhouette caused by light being bent and ultimately swallowed near the event horizon. The actual Schwarzschild radius lies just inside that shadow's edge. In this profound sense, we have now seen the boundary, even if not through a direct visual photograph. Because it is so incredibly distant, the entire phenomenon appears smaller in our sky than a donut placed on the moon would look to an observer on Earth. This is why imaging it required years of unparalleled coordination, enormous computing power, and the almost unimaginable precision of atomic clocks. Beyond the Schwarzschild radius lies a realm we can never directly observe. According to general relativity, once matter passes the event horizon, it is inevitably drawn towards the singularity at the very centre. The singularity is theorised as a point of infinite density, where the known laws of physics unequivocally break down. We do not currently know what truly transpires there. Some theories suggest it might be a tiny, infinitely curved region of space-time. Others propose that quantum effects could smear it out, or replace it entirely with something new, perhaps a Planck star or even a bridge to another universe. But as far as our instruments are concerned, it remains forever hidden. The Schwarzschild radius is not just a limit for light, it is a fundamental limit for cause and effect. No signal from inside can ever influence the outside. This means that the inner workings of a black hole are cut off from the rest of the cosmos in a very fundamental way. This is precisely why so much of black hole science must be conducted indirectly. We painstakingly measure the orbits of nearby stars, meticulously observe how superheated gas behaves, or detect the faint flickers of light caused by magnetic or gravitational turbulence just outside the event horizon. Sagittarius A is not unique in possessing a Schwarzschild radius of this size. Any object of 4 million solar masses would have the same value. What makes it unique is its privileged position in our galaxy, and the fact that we can study it in such intricate detail compared to others. Black holes with billions of solar masses possess much larger event horizons, sometimes exceeding the size of our entire solar system. In contrast, a stellar mass black hole might have a Schwarzschild radius of only a few kilometers. This is why scientists often describe black holes in terms of their mass, rather than their physical size. It is mass that fundamentally determines the radius in the first place. Once you know a black hole's mass, you know its Schwarzschild radius, and you also know something profound about the speed needed to escape from just outside it. The escape velocity equals the speed of light. That is the defining trait. For any other object, planets, stars, even neutron stars, the escape velocity is lower, meaning light can still get out. But at the Schwarzschild radius, the gravitational pull is too strong even for photons. Near Sagittarius A's Schwarzschild radius conditions are violently extreme even in its current quiet state. Magnetic fields twist and snap with incredible force. Charged particles spiral at near light speed, and space-time itself is dragged around by the black hole's immense spin. Even though Sagittarius A is relatively calm now, the zone just outside the horizon remains an extreme laboratory for fundamental physics. It's here that matter in the accretion flow heats to millions of degrees and emits the radio waves that the EHT so remarkably detected. It's here that flares of X-rays and infrared light sometimes burst forth when clumps of gas plunge inward, offering tantalizing glimpses into this otherwise hidden realm. In the mid-20th century, the centre of the Milky Way remained a largely inscrutable mystery. Throughout the 1980s, radio astronomy was the primary tool for investigating this strange cosmic source. observations with the Very Large Array VLA in New Mexico dramatically sharpened the view, revealing that Sagittarius A was not only compact but also variable, its radio output fluctuating over time. The next major leap involved pushing interferometry to an unprecedented scale. In the 1990s, scientists began linking radio dishes scattered across the globe using a technique called Very Long Baseline Interferometry (VLBI). This allowed them to synthesize a virtual telescope the size of Earth, dramatically improving resolution. By combining data from observatories thousands of kilometers apart, they could begin to measure Sagittarius A's apparent size, resolving it down to mere tens of microarc seconds across. Also in the 1990s, infrared astronomy truly came into its own thanks to revolutionary new detectors and adaptive optic systems that could effectively counteract the blurring effects of Earth's atmosphere. Over years of painstaking measurement, two independent teams meticulously mapped how stars moved in tight, incredibly fast orbits around the invisible point. NASA's Chandra X-ray Observatory, launched in 1999, revealed that Sagittarius A occasionally emitted bright X-ray flares, demonstrating it was not entirely dormant. The Spitzer Space Telescope mapped the crowded star fields and warm dust near the galactic center with unprecedented clarity. By operating above Earth's atmosphere, these space-based observatories bypassed atmospheric distortions and absorbed wavelengths, allowing scientists to gather cleaner, more detailed data than ever before possible. In the 2000s, submillimeter astronomy emerged as another vital tool. This part of the electromagnetic spectrum, falling between infrared and radio, is particularly adept at studying coal dust and the emissions from matter extremely close to black holes. The submillimeter array in Hawaii, and later the Atacama Large Millimeter Submillimeter Array ALMA in Chile, provided researchers with an even sharper look at Sagittarius A's immediate surroundings. These arrays, with their high-altitude locations and wide baselines, could detect exquisitely fine details in the faint emissions from the galactic center. The ultimate imaging challenge, however, was to capture the shadow of the black hole itself, a feat only possible by pushing VLBI to its absolute extreme. This is where the Event Horizon Telescope (EHT) entered the scene. Beginning in the 2010s, the EHT linked together a global network of radio observatories including ALMA, the South Pole Telescope, and others across North America, Europe, and Asia. Observations were conducted at a wavelength of 1.3 millimeters, a frequency specifically chosen because it can penetrate much of the galactic dust while offering exceptionally high resolution. In 2017, the EHT directed its full, synchronized attention to Sagittarius A. Processing the colossal volume of data took years, primarily because the black hole's appearance changes rapidly. Material whirling close to the event horizon moves at near light speed, causing the brightness pattern to shift dramatically in mere minutes. Combining data from multiple sites into a coherent picture required incredibly complex algorithms and careful averaging over time. Finally, in 2022, the EHT team released the first ever image of Sagittarius A, a blurry but unmistakable ring of light surrounding a dark central shadow, precisely what theory predicted for a black hole of its mass. Each step in this monumental journey reflects both astonishing technological progress and the unwavering persistence of the scientists involved. From the very first crude radio detections to a direct image of the event horizon silhouette, the journey spanned decades and demanded continuous innovations in instrumentation computing and observational techniques. New instruments such as the James Webb Space Telescope are now probing the galactic center with unmatched sensitivity in the infrared. While ongoing upgrades to the EHT promise even sharper images in the years ahead, the discovery of Sagittarius A has been a gradual, meticulous unveiling, each generation of instruments peeling back another layer of profound mystery. And with every improvement in our tools, we gain a clearer, more vibrant chapter in the living, evolving story of the Milky Way. Light does not simply travel straight through the cosmos. The fabric of space itself can bend and shape it, turning gravity into a natural lens. This phenomenon, gravitational lensing, is among nature's most remarkable tools, revealing details hidden deep within the universe. For those studying Sagittarius A, the supermassive black hole at our galaxy's core lensing offers rare, sharper glimpses into a region normally shrouded in darkness. Imagine placing a heavy bowling ball on a stretched rubber sheet. It sinks, creating a curve that redirects any rolling marble. In the same way, stars, black holes, and galaxies warp space-time bending light that passes near them. To a distant observer, that light appears magnified or distorted. Applied to Sagittarius A, this bending becomes not just a curiosity, it's a cosmic advantage. The galactic centre is packed with stars and gas clouds, its light obscured by thick dust. When another massive object passes between us and the black hole, gravity briefly clears that haze, letting us see further and finer than before. These lensing effects occur on many scales. Sometimes a single star orbiting close to Sagittarius A acts as a tiny micro lens, briefly magnifying background light. Other times, whole clusters or dense gas clouds warp light across wider regions. By studying these distortions, astronomers can trace light's original path and uncover what lies hidden in the galactic core. Even Sagittarius A itself bends the light of stars behind it, creating multiple images or stretched arcs. Measuring these distortions lets scientists calculate the black hole's mass and probe the mysterious space near its event horizon. Yet capturing such alignments is no simple task. Gravitational lensing demands an almost perfect lineup between observer lens and background source, rare and fleeting events in the ever-shifting galactic centre. That's why networks of telescopes across the globe monitor the region, continuously scanning for subtle brightness changes that signal a lensing moment. Early astronomers saw unexplained flashes but lacked the tools to interpret them. Now, with precise models and coordinated observations, researchers can detect and sometimes even predict these events. Even with our best telescopes, the region just beyond Sagittarius A's event horizon is vanishingly small from Earth. Lensing acts as a natural magnifier, enhancing our resolution, enough to study the shape of the accretion disk, the flow of magnetic fields, and the dynamics of orbiting matter. It can also amplify faint bursts of radiation, allowing astronomers to measure their timing and intensity with exquisite accuracy. Occasionally a flare's light may take two separate paths around the black hole before reaching us, producing a delayed echo that carries crucial information about space-time curvature. Gravitational lensing doesn't only affect visible light. Radio waves, infrared radiation, and even X-rays all follow the same curved trajectories. As a result, observatories across the electromagnetic spectrum, radio arrays, infrared telescopes, and orbital X-ray detectors have all detected hints of lensing near Sagittarius A. If the black hole were ever to flare more violently, lensing could magnify its brilliance far beyond the Milky Way, broadcasting its power across intergalactic distances, perhaps even to observers in other civilizations. In this sense, gravitational lensing is both a scientific instrument and a cosmic messenger, bending not only light, but also our understanding of the universe. And as technology advances, its full potential is only beginning to unfold. The next generation of observatories promises to turn gravitational lensing from a rare stroke of cosmic luck into a standard tool, one capable of unveiling the deepest secrets of the black hole at the heart of our galaxy. The light from stars orbiting near Sagittarius A must journey through Earth's thick, restless atmosphere before reaching our telescopes. While that atmosphere sustains life, it is disastrous for precision astronomy. Turbulent air pockets bend and scatter incoming starlight, making stars shimmer and blur. What looks like gentle twinkling to the naked eye becomes chaos for astronomers trying to trace the fine details of stars whipping around the black hole at our galaxy's centre. For decades, even the largest ground-based telescopes could not pierce this atmospheric distortion to produce truly sharp images. The revolution came with adaptive optics, a breakthrough that transformed observational astronomy. Instead of passively enduring atmospheric turbulence, scientists learned to fight back. The principle is beautifully direct. If the atmosphere bends, starlight use a flexible mirror that bends the opposite way, cancelling the distortion in real time. To measure that distortion, astronomers need a bright reference point, either a nearby star or an artificial one created by firing a powerful laser into the upper atmosphere. The laser excites sodium atoms about 90 kilometers above Earth, forming a glowing guide star. Computers then analyze how this artificial light warps as it travels downward, instantly calculating how the telescope's mirror must flex to correct it. The mirror adjusts hundreds of times per second, restoring clarity once thought impossible. When adaptive optics was first turned towards Sagittarius A, it changed everything. Fuzzy smudges of light transformed into crisp, defined stars. Astronomers could finally watch individual stars carve tight orbits around the invisible black hole, proving its immense gravity beyond doubt. They could now dissect starlight into its component wavelengths to measure speed, temperature, and chemical makeup with exquisite accuracy. The leap in clarity was like moving from foggy glass to high-definition vision. Even so, observing the galactic centre remains daunting. Dense, interstellar dust blocks most visible light, forcing astronomers to operate primarily in the infrared. Fortunately, adaptive optics works just as well in those wavelengths. The combination of infrared capability and real-time correction has unlocked some of the most remarkable discoveries in modern astrophysics, including the detection of gravitational redshift from stars like S2 and the precise mapping of their orbits. The technology's precision is astonishing. Deformable mirrors, thin, flexible layers of glass or metal are manipulated by microscopic actuators that move less than a hair's width, yet those tiny adjustments completely reshape the image. Over the years, the system has grown ever more refined. Early versions corrected broad distortions but missed finer details. Modern designs use multi-conjugate adaptive optics, which targets multiple layers of the atmosphere at once, each with its own mirror and guide star. This layered correction creates sharp, stable images across wider fields of view. For Sagittarius A, it means researchers can now look for subtle changes, flickers of light, slight positional shifts that may signal faint gas clouds, or hotspots spiraling close to the event horizon. Adaptive optics has also been paired with interferometry, which links multiple telescopes to push resolution even further. Together they allow scientists to examine regions once thought unreachable from the ground. What began as an attempt to fix Earth's blurry skies has become an indispensable gateway to the very edge of a black hole. The success of adaptive optics reshaped astronomy. It is now standard in major observatories worldwide, improving images of everything from distant galaxies to nearby exoplanets. But nowhere has its impact been deeper than at the Milky Way's core. By stabilizing Earth's view, it transformed chaos into clarity, turning the once murky center into a precisely charted arena where gravity reigns supreme. Combined with the immense mirrors of ground-based observatories and the stability of space telescopes, this technology forged a powerful synergy, one that brought the universe's most extreme objects into sharper focus than ever before. In 2019, the world witnessed a scientific milestone, the first image of a black hole. The target was not Sagittarius A, but 87, a behemoth, 6.5 billion times the mass of the Sun, sitting 55 million light-years away. Its enormous size made it an ideal first candidate. Larger black holes produce larger shadows and evolve more slowly, allowing astronomers time to capture stable images without rapid brightness changes blurring the results. No single telescope could possibly resolve such a tiny distant target. To do it, scientists created an Earth-sized virtual telescope, the Event Horizon Telescope EHT. This global network linked radio observatories across continents, synchronizing them with atomic clocks of unimaginable precision, so accurate they'd lose less than a second in millions of years. Each site recorded petabytes of data that had to be physically flown to central supercomputers for processing. In April 2017, under nearly perfect weather conditions at all sites, every dish in the network turned toward M87, capturing radio waves emitted by matter swirling near the event horizon. When the data finally converged, teams of researchers working independently to avoid bias reconstructed the image from delicate interference patterns. On April 10, 2019, the result was unveiled: a glowing orange ring surrounding a dark centre, the unmistakable shadow of a black hole. That cosmic donut instantly became an icon of human curiosity. It was visual proof of Einstein's general relativity in its most extreme form. The size and symmetry of the ring matched theoretical predictions almost perfectly. The bright crescent revealed matter racing near light speed, its glow intensified by relativistic Doppler, boosting one side appearing brighter because it was moving toward us. The image confirmed that millimeter wave interferometry could indeed resolve an event horizon, silencing decades of doubt. The triumph of M87 was more than a photograph. It was a blueprint. It showed that humanity could coordinate a global array of telescopes to glimpse the unseeable. The project united hundreds of scientists from around the world, working across languages and continents with a single goal: to reveal the heart of darkness. Their success set the stage for the next, even harder challenge imaging Sagittarius A itself. Our black hole is smaller and changes far faster than M87's, but it also looms larger in our sky. The methods refined through M87 paved the way: better algorithms, more telescopes, sharper timing. The first image proved our models of gravity correct, and with it the EHT earned the confidence to push deeper. Since then, the network has grown, adding new observatories and observing at multiple wavelengths to probe black holes from different angles. Plans are already underway for next-generation EHT arrays, possibly extending into space. These could capture not just still images, but time-lapse movies of matter spiraling inward, recording in real time the violent choreography of energy and gravity at the brink of the unknown. The M87 image transformed black holes from theoretical abstractions into tangible cosmic realities. What once lived only in equations became something the human eye could finally see: the edge of physics itself glowing against the infinite dark. Imaging Sagittarius A was in many ways an order of magnitude harder than imaging M87. Our target is smaller, so the radio glow around it presents a tinier silhouette about the size of a donut on the face of the moon. Worse, it is far more restless. M87's appearance changes over days to weeks. Sagittarius A morphs over minutes to hours. Gas orbits so close to the event horizon that hotspots can complete a loop in mere minutes. By the time you finish collecting data to build an image, the source is already changed. M87 was like photographing a lighthouse. Sagittarius A was like trying to capture a candle flame in a gale with a long exposure. The journey its radio waves take to reach us is also harsher. M87's signal crosses intergalactic emptiness. Sagittarius A sits in the crowded, dusty core of the Milky Way. Along our line of sight, turbulent plasma scatters and blurs the signal, imposing a shimmering distortion that must be modelled and removed. Even with careful corrections, some fine structure is inevitably lost. Synchronization already demanding for M87 becomes unforgiving here. Every EHT dish from Chile and Hawaii to Europe and the South Pole must record the very same rapidly changing target at the very same moments. Atomic clocks lock the network together, but weather can break that lock. One site's clouds jeopardize everyone's night. Coordinating this global symphony means getting every instrument on different continents to play the same measure in perfect time while the score itself keeps changing. The image reconstruction problem had to be reimagined from the ground up. Traditional algorithms assume the source is quasi-static during the observing window. Sagittarius A violates that assumption. The EHT teams developed new methods that generate vast ensembles of candidate images and search for features that persist across them, statistical anchors that survive the black hole's rapid variability and the network's uneven coverage. Instead of chasing a single snapshot, they assembled a time-average portrait tested against thousands of possibilities. Signal strength posed another obstacle. M87's bright, steady accretion flow is a roaring campfire. Sagittarius A is a faint candle at noon. At shorter wavelengths, the galactic centre's scattering smears the image. At longer wavelengths, scattering eases, but angular resolution worsens. The EHT had to find a sweet spot that balanced resolution, clarity and brightness, then peel away contaminating emission from nearby stars, clouds and compact radio sources. Months of analysis filtered and cross-checked the data to isolate the black hole's own signature. By the end, the collaboration had processed petabytes of recordings, run thousands of simulations, and stress-tested every algorithmic choice. Only when different pipelines converged on the same answer again and again did the team accept the result. Released in 2022, the image revealed a familiar shape, a blurry, lopsided ring surrounding a dark interior, reminiscent of M87, yet fuzzier and more variable. The similarity mattered. It meant gravity in both systems sculpts light in the same fundamental way, even as the details differ. The fuzziness also mattered. It encoded all the difficulty that made Sagittarius A the most stubborn target in high-resolution astronomy. Celebration was justified, but nobody on the team thought the job finished. The first image confirmed much of what theory predicted while leaving critical questions unresolved. Spin for one. A black hole's rotation can range from nearly zero to near the theoretical maximum reshaping orbits, energizing outflows and subtly distorting the photon ring. But a time-averaged, rapidly variable image is a blunt tool for reading that signature. The spin may be imprinted in the full data stream hidden in correlated Flicker's phase relationships or polarization patterns, but it is not obvious in the debut picture. Orientation is the next mystery. A black hole has no top yet. It has a spin axis. For M87, a bright extended jet gives away the geometry. Sagittarius A lacks such a clear pointer. If mild outflows exist, they are buried in the glare and clutter of the galactic centre. Without a jet to act as a cosmic arrow determining the tilt and direction of the spin axis is far more difficult. Magnetic fields are another frontier. Polarization, how light's electric field is oriented, traces magnetic structure with exquisite sensitivity. The first Sagittarius A images emphasized total intensity. Polarization campaigns are now underway to map the magnetic choreography, feeding throttling and twisting the accretion flow. Those data may reveal how plasma threads the event horizon's edge, and whether magnetic reconnection drives the sudden flares we see. Time resolution is the holy grail. The 2022 image is a time average necessary because the array must observe for hours to build a picture, while the source morphs in minutes. What we crave are movies' frame-by-frame reconstructions that track hotspots racing along relativistic orbits, flares erupting and fading shadows wobbling under lensing and turbulence. That requires more baselines, better coverage, faster cadence, and new algorithms that embrace change rather than smooth it away. Accretion physics remains murky. How much matter is actually falling in? How do inflows and outflows balance over months and years? Is Sagittarius A starved by stellar winds or intermittently fed by clumps of gas? The current images can't yet pin down the flow's thermodynamics with precision. Multi-wavelength campaigns coordinating radio millimeter infrared and X-ray observatories are essential to connect structural images with energetic events. General relativity passed this test, but the error bars still leave room for exotic alternatives. The shadow size agrees with predictions based on the black hole's measured mass, yet tighter constraints could rule out or support subtle deviations in extreme gravity. Sharper polarized and time-resolved images will tighten those bounds, turning Sagittarius A into a laboratory for theories of space-time itself. Finally, the interstellar medium continues to meddle. As the signal threads the Milky Way's turbulent plasma, it is blurred and refracted. Corrections are good, not perfect. Observing at multiple frequencies, modelling the scattering screen in detail, and adding longer baselines, especially space-based ones, will help disentangle intrinsic structure from propagation noise. None of this is hypothetical. The EHT keeps growing, adding stations, upgrading receivers, and expanding to new wavelengths. Polarimetric maps are improving. Coordinated campaigns with infrared facilities track flares in real time as the EHT records the structure that produced them. Ambitious proposals envision radio dishes in orbit, linking with ground arrays stretching baselines beyond Earth's diameter and sharpening vision enough to film gravity at work. The first portrait of Sagittarius A gave our black hole a face. It did not give us its autobiography. Spin orientation, magnetic architecture feeding habits, and the choreography of hotspots remain open chapters. That is not a failure. It is the signature of progress. We have crossed the threshold from inference to sight, from equations and simulations to images and soon to movies. What began as a seemingly impossible task coordinating a planet's worth of telescopes to photograph a flickering ring of light has become a method. The method will be refined, the questions will get sharper, and the next images will not merely confirm what we believe, they will show us what we do not yet know how to ask. Could anything orbit inside a black hole's event horizon? By definition, the horizon is a sealed boundary once crossed. Nothing light included returns to tell the tale. Classical general relativity gives a stark answer no. Within the horizon, every possible path in space-time tips inward. Matter and radiation don't circle. They plunge spiraling toward a singularity where the known laws of physics break down. Modern physics refuses to leave the story there. If quantum mechanics truly governs everything, then the singularity may be a mirage, an artifact of incomplete theory. In quantum gravity, pictures, the central point of infinite density, could be replaced by an ultra-compact but finite core, a bizarre state that stores all the black hole's mass and information. If space-time becomes granular or otherwise modified at extreme scales, the interior might host regions where particles or fields execute loops or quasi-periodic motions. We would never see those motions from the outside, they remain hidden behind the horizon, but mathematically orbits of a new kind are not forbidden. Some speculative models go further, proposing layered interiors. Cross the event horizon, and you might encounter an inner horizon, a second boundary marking a new regime of space-time. In these scenarios, often tied to rotating Kerr black holes, light and particles can on paper follow stable cyclical paths around a ring-shaped singularity. Such paths bear little resemblance to planetary orbits. They are choreography dictated by extreme geometry, not Newtonian gravity. Add exotic matter to the mix, hypothetical forms that behave unlike familiar atoms, and the menu of possibilities widens. String theory sketches picture interiors crisscrossed by vibrating strings, or membranes, where motion is best described as repeated loops in warped space-time rather than neat ellipses. Quantum fields add more weirdness. Even in empty space, quantum mechanics allows flickering pairs of virtual particles to appear and annihilate. Near the horizon, these effects underwrite Hawking radiation, the slow leakage by which black holes evaporate over unimaginable times. Inside, similar fluctuations could create a roiling sea of ephemeral activity patterns that might resemble orbits if we could witness them, but they vanish almost as soon as they arise. A bolder conjecture reframes the interior entirely. Perhaps what falls in is diverted into a new region of space-time or an entirely separate universe. Wormhole solutions to Einstein's equations hint at tunnels connecting distant places or even different cosmic domains. A traversable, stable wormhole is almost certainly ruled out by realistic physics, but if such a conduit existed, orbit-like motion inside would mean winding through curved tunnels, not circling a mass. Another perspective centers on information. The black hole information paradox asks whether the details of what falls in are truly lost. Some proposals suggest the information persists in scrambled non-local patterns at or within the horizon. If such patterns evolve, they could trace cycles or repeating behaviors, dynamics of information rather than of matter. Loop quantum gravity, which models space itself as built from discrete units, imagines that collapse could halt and bounce, replacing the singularity with oscillations of geometry. In that view, interior regions might swing around one another, producing motion that looks cyclic, because the fabric of space is doing the oscillating. A few cosmological speculations even suggest that black holes seed baby universes. To an internal observer who can never be the interior might resemble an expanding cosmos with its own structures. All of these audacious ideas run into the same brick wall the event horizon blocks direct observation. We will never peer inside with a telescope. Our only tools are mathematics simulations and indirect clues from how the black hole sculpts the space-time we can see. That doesn't make the thought experiments idle. On the contrary, wrestling with the interior sharpens our theories and forces us to test the limits of gravity, quantum mechanics, and the nature of information. Even so, the evidence that Sagittarius A is a supermassive black hole is overwhelming. Stars near the galactic center whip around an invisible point with velocities and orbits that require an extraordinarily compact mass. Emission from hot gas behaves exactly as expected for material plunging toward an event horizon. Yet science is at its best when it keeps alternatives on the table until the data make them untenable. Could Sagittarius A be something stranger? Dark matter is the first suspect. This unseen substance shapes galaxies yet doesn't emit or absorb light. Could a dense clump of dark matter mimic a black hole's pull? In practice, no standard dark matter hardly interacts with itself and lacks a way to shed energy, so it won't collapse into a tiny solar system-sized object. The central mass in the Milky Way is too compact. More speculative dark matter candidates, self-interacting or ultralight varieties, could in theory form exotic cores without horizons. Such an object would have some sort of surface. In falling, material would slam into it, releasing a transient glow. We've seen no convincing evidence of such impacts. Instead, matter appears to vanish as if crossing a true horizon. A boson star is another exotic contender. Built from ultralight bosons that can occupy the same quantum state, a boson star could be extremely compact and dark, bending light to create a shadow-like feature. At current resolution, its image might resemble a black hole's, but subtle signatures, how brightness varies, how nearby matter moves should eventually differ. Disentangling those differences demands sharper images, tighter timing, and polarization maps that trace magnetic fields. Enter the Grava star, which replaces the singularity with a shell of exotic matter, surrounding an interior filled with vacuum-like energy. From afar, a Grava star would imitate a black hole's gravity and bend light similarly, but with no event horizon, just a surface perched barely outside it. Again, the telltale would be energy from infalling material hitting that surface. No definitive flashes have been seen, though the absence could reflect faint, steady feeding or limited sensitivity. String theory fuzzballs take a different tack. The entire object is a tangle of fundamental strings with no empty interior and no singular point. From a distance, a fuzzball looks like a black hole. Up close, it's all structure. Wormhole mouths make a cameo in some models, tempting but extremely speculative. The problem with every alternative is empirical Sagittarius A behaves like a black hole to every test we can currently apply. Stellar orbits, spectra variability, and the Event Horizon Telescope's ring and shadow image all line up with general relativity's expectations. No observation has produced a clean, unambiguous non-black hole signature. That doesn't end the discussion, it sets the bar. Future observations, higher resolution, multi-wavelength, time-resolved polarized, must either keep confirming the black hole picture or force us to revise it. Understanding what sits at the Milky Way's center also helps explain how the galaxy itself took shape. The inner few light years are nothing like our sun's quiet suburb. Gravity there is ferocious and stars dart through space at incredible speeds, some completing orbits in just years. In the galaxy's youth, more than 13 billion years ago, the Milky Way was a chaotic mashup of gas clouds and merging fragments. Sagittarius A likely began as the remnant of an early massive star or a small black hole formed in those turbulent times. Over eons, gas inflows and stellar migrations delivered mass to the center, and the black hole grew. Its gravity deepened the central potential, well encouraging the buildup of the dense stellar bulge we see today. Feedback from active phases, brief outbursts when accretion spiked, may have stirred and heated gas influencing star formation and the distribution of heavy elements. In this sense, Sagittarius A is both archivist and architect, a record of the galaxy's past and a shaper of its present structure. Where does that leave the question that started this journey? Could something orbit inside the event horizon? In classical relativity, no. In quantum-informed models, orbit-like behaviour might exist as internal cycles of geometry fields or information forever hidden from us. The event horizon turns the interior into a conceptual laboratory, not an observational one. Meanwhile, everything we can measure outside the horizon continues to point toward an authentic black hole. The work ahead is clear. Better images at multiple wavelengths will test the size and shape of the shadow against general relativity, with harsher precision squeezing out room for exotic alternatives. Polarization maps will reveal magnetic field structures that feed or choke the black hole and may illuminate how flares ignite. Time-resolved reconstructions, true movies of hotspots racing at relativistic speeds, will help decode spin orientation and the choreography of the accretion flow. Each improvement sharpens the line between what must be and what might be. We may never look inside, but by perfecting what we can see, the lensed ring, the flickers of radiation, the dance of nearby stars, we learn what the interior has to be consistent with. In that way, the horizon's silence becomes a kind of speech. It tells us indirectly but insistently how gravity and quantum rules negotiate at the brink. Whether Sagittarius A is precisely the black hole we think it is, or the gateway to deeper surprises, the path forward is the same. Keep asking better questions, and keep building the tools that let the universe answer. Simulation suggests that even in the Milky Way's turbulent youth, a central black hole could vigorously stir the surrounding gas. That stirring cuts two ways. In one mode, gravity funnels material inward, feeding the black hole and accelerating the rise of the stellar bulge. In another, an active black hole drives powerful winds and outflows, blasting gas outward and quenching star formation in select regions. Which effect wins depends on how fast the black hole is growing and how much energy it dumps into its environment. Across many galaxies, observers see a tight correlation between the mass of the central black hole and the mass of the galactic bulge. This elegant scaling hints at co-evolution, black holes and bulges growing in tandem, each shaping the other's fate. That relation doesn't prove Sagittarius has single-handedly sculpted the Milky Way, but it strongly implies an intimate feedback loop between our black hole's growth and the galaxy's development. If Sagittarius A once exerted strong influence, the likely epochs were those when it was far more active than today, pumping vast energy into the inner galaxy, delaying runaway star formation, and buying time for the Milky Way's spiral architecture to mature more gradually. Even the vast, faint Fermi bubbles arcing above and below the plane suggest that the black hole's reach can extend into the halo, rearranging gas on truly grand scales. Gravity's grip is strongest near the core and weakens with distance, yet the enormous central mass concentration black hole, plus dense nuclear star cluster, may have helped stabilize the Milky Way's bar, a bright, elongated structure that cuts across the center and can channel gas inward. That bar likely plays a dual role, feeding fresh material for new stars and supplying the slow, incremental growth of the black hole. Through that control of where and when stars ignite, Sagittarius A may also have influenced the chemical evolution of the galaxy. Clearing gas in some neighborhoods stalls the recycling of heavy elements, carbon, oxygen, iron into new generations of stars. Over billions of years, such subtle regulation could contribute to today's rich patchwork of stellar chemistries across the disk and bulge. Still, a central black hole's reach has limits. The outer disk where the Sun lives is governed less by the core and more by spiral density waves, gas dynamics, and the galaxy's dark matter halo. Sagittarius A likely shaped the inner bulge and nuclear regions most. The sprawling, graceful arms owe more to broader processes that ripple through the disk. To reconstruct our own past, astronomers study galaxies at different stages of life, searching for snapshots that echo the Milky Way's earlier chapters, and for the faint fingerprints of central black holes helping steer their hosts. What if there had never been a central black hole? Some models predict a smaller or less coherent bulge, perhaps a looser inner structure. Others argue the influence of a black hole is a complex feedback loop rather than a top-down script. The truth is probably a moving target. Sometimes Sagittarius A rode along as a relatively passive passenger. At other times it drove, sending energetic ripples through the galactic heart and leaving marks we can still trace today. While we probe the past, the future of observing Sagittarius A is accelerating. Across the world, engineers, astronomers, and computer scientists are building the next generation of instruments that will make the current Event Horizon Telescope EHT look like a prototype. The now iconic image of our black hole came from a heroic global collaboration, but the tools that produced it were already aging the day the picture debuted. In astronomy, data gathering and publication are separated by long cycles. By the time results hit the world stage, the hardware has marched on. The most dramatic leap ahead is simple in concept: add more telescopes. Interferometry's resolution and image fidelity improve with more baselines, more distances and orientations between stations. Today's EHT has unavoidable holes in its virtual Earth-sized mirror. Geography, funding and politics dictate where dishes can live. New sites in undersampled regions, especially in the southern hemisphere, would fill in missing pieces and sharpen the portrait of Sagittarius A. Plans under discussion include strategically placed dishes in Africa to bolster north-south coverage, plus stations on remote Pacific islands, or even mobile platforms at sea to catch radio wave patterns that fixed observatories miss. Each new location unlocks finer detail in the faint light skimming the black hole's edge. Then comes the next frontier space VLBI, very long baseline interferometry, with one or more radio antennas in orbit stretches the virtual dish beyond Earth's diameter. Space antennas could partner with ground arrays to push resolution into territory where we start to see change unfold over hours, not months. Space. VLBI has been tested but not yet optimized for black hole imaging at millimeter wavelengths. Doing so would be a technical moonshot with a spectacular payoff. Data handling will transform as well. The EHT already generates staggering volumes of raw data. Future arrays aim for faster, higher capacity recorders, and where feasible, direct intercontinental streaming over ultra-high-speed fiber. Near real-time correlation would shrink the months-long wait between observation and image. On the processing side, new algorithms and machine learning will sift interference patterns more robustly, recover faint features more reliably, and flag interesting changes as they happen. AI won't replace physical modelling, but it can triage and denoise with speed and consistency that help humans focus on the physics. The observing strategy will broaden too. Today's flagship wavelength is 1.3 mm, a sweet spot that balances atmospheric transparency with sharpness, but it's only one slice of the spectrum. Multiband observing adds context. Shorter wavelengths, e.g. 0, 8 to 7 mm, promise crisper resolution near the event horizon, albeit with more demanding hardware and stricter weather constraints. Longer wavelengths trace cooler gas farther out, and feel less of the interstellar scattering that blurs the finer structure. Together, simultaneous bands act like colour imaging for accretion physics, revealing temperature density and motion across layers of plasma. Longer campaigns are another key. The first Sagittarius A image came from just a few nights the price of needing perfect weather everywhere. Smarter scheduling, better forecasts, and a bigger network increase usable time. More hours of clean data mean we can chase the dream of black hole movies' time-resolved reconstructions that show hotspots orbiting, flares igniting, and the ring breathing as turbulence and gravity wrestle. Cross-pollination with other instruments will deepen the picture. The Square Kilometre Array SKA, rising in Australia and South Africa, won't match the EHT's resolution, but it will add an enormous sensitivity ideal for detecting faint extended features, small flares, or whisper-thin streams of plasma that feed the beast. Coordinated campaigns let the EHT see structure, while SKA measures the faint background tying the near-horizon drama to the broader environment. Looking even farther ahead, some scientists envision lunar stations for EHT-style work. The Moon's airless environment eliminates atmospheric distortion and allows round-the-clock duty cycles unconstrained by Earth's day-night rhythm. A lunar Earth baseline would expand the virtual mirror dramatically. It's ambitious but not science fiction. Polarization mapping is another frontier charging ahead. The first M87 image included a polarization overlay tracing magnetic field lines around the black hole. Sagittarius A polarization campaigns are underway. Stronger, cleaner polarization data could reveal how fields twist, reconnect and accelerate particles, clues to why our black hole is comparatively quiet today and what lights its brief, bright flares. As the network grows sharper, we can compare black holes as a population. Does appearance depend most on mass spin feeding rate magnetic topology, or some coupling among them, with multiple sources imaged at comparable quality patterns will emerge? Today's milestone portrait is almost guaranteed to be overtaken by a sharper, more detailed view, and eventually by time-lapse sequences that catch our galaxy's strangest object in motion. Among the most coveted prizes is the spin of Sagittarius A. Spin is a fossil record high-aligned spin hints at steady disk-fed growth. Low or oddly tilted spin points to chaotic accretion or past mergers. But spin hides. We infer it from how light and matter behave in warped space-time. One of the most promising paths is X-ray polarimetry, which measures the orientation of X-ray waves. Scattering strong gravity and magnetic fields polarize light in distinctive ways. Near a spinning black hole frame dragging the twisting of space-time itself, subtly rotates polarization angles and alters how photons scatter before they escape. Matter spiraling inward heats to emit X-rays. Those photons ricochet through curved space-time and tangled fields, imprinting the geometry and the spin onto their polarization. Measuring that imprint requires exquisitely sensitive detectors above Earth's atmosphere. NASA's Imaging X-ray Polarimetry Explorer, launched in 2021, is pioneering this domain across many targets. Sagittarius A is faint in X-rays except during brief flares, but those flashes offer windows where polarization may be strong enough to decode. Next-generation concepts aim for larger collecting areas, sharper imaging to isolate the black hole from the crowded galactic center, and faster timing to track polarization swings during a single flare. Watching the polarization angle precess as hotspot orbits would reveal not only spin magnitude but also the tilt of the spin axis relative to the galaxy. Spin is not necessarily fixed. If Sagittarius A drifts into a livelier feeding phase, the angular momentum of new and falling gas could spin it up or break it depending on orientation. Long-term polarimetry could turn spin from a static parameter into a time-evolving measurement. These data also stress-test general relativity in the strong field regime. The theory predicts specific polarization signatures near a spinning horizon. Deviations might hint at new physics, modified gravity, quantum effects at the brink, or unexpected magnetic geometry. Polarization helps disentangle gravity's fingerprint from magnetisms. Both polarize light, but with different energy dependence. By comparing polarization across X-ray energies, researchers can separate the gravitational lensing and frame dragging effects from those produced by twisting magnetic fields and reconnection. Farther down the road, interferometric X-ray polarimetry could map polarization at astonishing resolution, identifying precisely where flares originate, a near-horizon hotspot, a shock in the accretion flow or a magnetic reconnection site. Finally, there's the music of space-time gravitational waves. A quiescent supermassive black hole like Sagittarius A won't ring loudly enough for current ground-based detectors. To hear it, we need something dramatic. Two supermassive black holes merging a massive star being torn apart, or most promisingly an extreme mass ratio in spiral emery, a stellar mass black hole or neutron star spiraling slowly into Sagittarius A. EMRIs radiate at low frequencies below the reach of ground-based detectors tuned for stellar mass collisions. While this script stops short of the specific mission details, the broader point stands if and when we detect the delicate, long-lived song of a small body spiraling into our black hole. Its waveform will encode the space-time geometry with exquisite fidelity. Another path to spin orientation and the detailed shape of the gravitational well. Put together, these advances more baseline space and perhaps lunar stations multiband campaigns, real-time processing, deeper polarization, and the promise of low-frequency gravitational waves transform Sagittarius A from a single blurry snapshot into a laboratory. We will test how black holes co-evolve with galaxies, how magnetic fields feed or quench accretion, how spin records a lifetime of meals and mergers, and how gravity itself behaves at the edge of the knowable. The first image gave our black hole a face. The next wave will give it a heartbeat and a history. A future space-based gravitational wave observatory, most notably the European Space Agency's LISA laser interferometer space antenna, is built to hear the slow, deep music our current ground detectors can't. Instead of mirrors anchored on Earth, LISA will fly 3 spacecraft millions of kilometers apart, linked by exquisitely stable laser beams. That vast silent triangle in space targets millihertz, frequencies the realm of extreme mass ratio in spirals EMRIs, where a stellar mass black hole or neutron star takes its slow, fatal spiral into a supermassive black hole. If an object begins such a long goodbye around Sagittarius, a LISA could detect the signal years before the final plunge, enough warning to coordinate an armada of telescopes from radio through X-rays to watch the drama unfold in unprecedented detail. More exotic possibilities exist too. A massive star collapsing near the galactic center, a neutron star torn apart by extreme tides or compact objects colliding in a sudden flash. Those cataclysms would sing at higher frequencies within reach of ground-based detectors, but they're rare and unpredictable. Catching one near Sagittarius A would be a stroke of cosmic luck. Still, if we do, the scientific payoff would be extraordinary precise measurements of mass and spin, strong field tests of general relativity, and searches for subtle deviations that might hint at new physics, perhaps even clues to how space-time behaves just outside the event horizon. The unique power of gravitational waves is their honesty. Light can be scattered, absorbed, or scrambled by gas, dust, and magnetic fields. Gravitational waves pass through matter nearly unimpeded. They carry a direct, unfiltered imprint of orbital motion and space-time curvature, but extracting those whispers requires patience and persistence. Signals can last months to years and are buried deep in noise, demanding continuous observation and sophisticated analysis. That's why LISA targets the 2030s building, testing and flying. A laser-linked observatory millions of kilometers wide is an engineering epic. Meanwhile, the ground game advances. Next-generation facilities like Cosmic Explorer in the US and the Einstein Telescope in Europe aim to be far more sensitive than today's LIGO and Virgo. They won't catch the slow inspirals into Sagittarius A. Their sweet spot is higher frequency, but they can capture short, violent bursts. Pair that capability with LISA's low-frequency hearing, and we'll survey the full symphony, the drawn-out bass notes of EMRIs, and the sharp treble of sudden disruptions. Looking ahead, a network of space-based detectors placed at different points in the solar system could triangulate sources with pinpoint accuracy, letting us swing electromagnetic telescopes towards Sagittarius A in real time. Listening to the heartbeat of the Milky Way's central black hole is no longer science fiction. The technology is marching toward it step by deliberate step. Far beyond our planning horizons lies a different kind of spectacle. In roughly 4 billion years, the Milky Way and Andromeda M31 will collide. They're already on a slow-motion intercept at about 110 kilometers per second leisurely, by human standards decisive on cosmic scales. Popular imagination conjures stars smashing together. Space is mostly empty. Almost all stars will miss. The true upheaval is gravitational spiral arms twisted gas clouds flung into arcs and bridges, stellar orbits scrambled, and both galaxies' central black holes, Sagittarius A and M31's giant, dragged toward each other by dynamical friction, a cosmic braking provided by background stars and dark matter. As the merger proceeds, torrents of gas and disrupted stars will pour into both galactic centres, likely igniting active galactic nuclei. Each core could blaze brighter than its host's entire stellar population, fed by matter spiralling toward the horizons. The graceful disks we know will stretch and warp, then settle into a new form, probably a massive elliptical galaxy with fewer signs of spiral structure. Many stars will trade their tidy circular paths for scrambled eccentric orbits. Some will be hurled into the intergalactic dark. Planets around unlucky stars could be nudged onto dangerous trajectories, or even exiled to deep space where worlds quickly freeze and atmospheres collapse. At the heart of the newly forming galaxy, Sagittarius A and M31's black hole will orbit each other for tens of millions of years, radiating gravitational waves that to far future detectors will be unmistakable. The pair will spiral inward, losing orbital energy until the two horizons touch. The final merger will unleash a colossal pulse of gravitational energy and leave behind a single, even more massive black hole, tens of millions of solar masses or more, depending on how much fuel the chaos provides. The newborn spin will encode the entire dynamical history, the orientations and speeds of both progenitors, written into one rotating engine. For any life that endures somewhere in the merged galaxy, the view will depend on distance from the maelstrom. Near the core, radiation from infalling matter could sterilize worlds and strip atmospheres. Farther out, the changes would be more aesthetic constellations, resketched spiral tracery, replaced by a smooth halo of stars, occasional flares briefly outshining the galaxy. And yet the odds that Earth will watch this pageant are slim. Long before the sun's gradual brightening and inevitable step in stellar evolution will likely render our planet uninhabitable within 1 to 2 billion years. Oceans could evaporate, the atmosphere could bleed water to space, the surface could bake. The Milky Way Andromeda drama will proceed regardless, but our home world may already be a silent cinder. Even setting the sun aside, a major merger scrambles stellar neighbourhoods. The solar system could drift inward toward the bustling core or be flung outward to the quiet periphery. Most likely it survives but relocates. In a worse roll of the cosmic dice, a near pass by another star perturbs planetary orbits, destabilising the clockwork we take for granted. And then comes the sun's own crescendo. In about 5 billion years it will swell into a red giant, possibly engulfing Earth. Whether our planet is swallowed or merely scorched, the surface story ends there. If humanity or any descendant intelligence exists, then it will almost certainly live elsewhere on engineered habitats, distant planets, or even in other galaxies. The true witnesses may stand far from any original cradle. There remains a slender poetic possibility that Earth survives the sun's expansion and the gravitational rough and tumble with its orbit mostly intact. If so, the sky would stage a masterpiece in slow motion. Over millions of years, Andromeda would grow from a faint smudge to a dominating whirl of stars and dust lanes. As the galaxies interpenetrate, the heavens would fill with haze and filaments, then reorganize into incandescent streams and clustered knots of newborn stars. The central region would shine with startling brilliance, while powerful jets and shock-brightened clouds betray the central engines feeding on fresh fuel. The sky would not simply be beautiful, it would be alive, changing on timescales visible across many generations. Mergers catalyze starbursts. Gas compresses, clouds collapse, and clusters of hot blue stars bloom across the merging system. From stable vantage points, the night would sparkle with newly minted clusters, supernovae, and luminous nebulae. It would look like a cosmic festival, except the festival lasts millions of years, outliving civilizations and even species. Whether anyone is watching is an open question. The universe is indifferent to audiences. Galaxies will collide, the black holes will merge, and cosmic evolution will continue whether or not Earth persists. Between the long future of mergers and the nearer future of instrumentation lies a powerful synthesis, gravitational waves and light combined. Lisa's early warning for an emery at Sagittarius A would let us coordinate multi-messenger campaigns, radio arrays mapping jets and outflows millimeter interferometers, imaging near-horizon structure, infrared telescopes tracking hotspots and flares, X-ray and gamma-ray missions catching high-energy bursts. Each messenger fills a gap. Gravitational waves outline the geometry and masses. Polarization maps trace magnetic fields. Spectra reveal temperatures, densities, and chemical fingerprints. Time variability exposes orbits and shocks. Together they tell a single coherent story of space-time matter and energy at the brink of the known. To get there, the observatories themselves must evolve. Adding more stations to Earth's millimeter arrays will fill gaps in the UV plane, improving image fidelity. Establishing dishes in undersampled regions, Africa Pacific Islands, even mobile sea platforms builds longer and differently oriented baselines. Pushing into space, VLBI at millimeter wavelengths stretches the virtual dish beyond Earth's diameter, reaching angular resolutions fine enough to watch Sagittarius A change on hour-long timescales. Data pipelines will shift from record and ship to near real-time correlation as ultra-fast fiber links and better clocks become standard. Machine learning tools will denoise flag anomalies and expedite reconstructions, accelerating science without replacing careful physical modelling. Observing at multiple wavelengths simultaneously adds depth. Shorter millimeter bands sharpen the view right at the photon ring, though they demand stricter weather and more sensitive receivers. Longer wavelengths trace cooler, more distant gas while mitigating interstellar scattering. Think of it as adding colour channels to a black and white portrait. The structure stays, but the physics gains dimension. With longer campaigns and better weather windows will assemble not just pictures, but movies. Time-resolved sequences catching hotspots orbiting at relativistic speeds, flares rising and fading, and the lensed ring subtly breathing with turbulence. Polarization is critical. The magnetic fields threading the accretion flow can channel plasma launch winds and possibly power jets. Polarization maps show how those fields twist and reconnect, and how gravity's frame dragging rotates the plane of polarization near a spinning horizon. In X-rays missions like XPE open a new diagnostic. The polarization angle and degree across energies can untangle gravity's imprint from magnetisms, constrain the spin and tilt of Sagittarius A, and test general relativity where space-time is most warped. Next generation X-ray polarimeters with larger collecting areas and faster timing could watch polarization swing within a single flare, turning spin from a static number into an evolving trackable quantity. Finally, the gravitational wave path reaches beyond emeries. If in the remote future Sagittarius A merges with Andromeda's central black hole, the low-frequency roar will be deafening to instruments far more sensitive than anything we can build today. In the nearer term, even a single MRI detection will be transformative. The waveform encodes the space-time geometry with exquisite precision. By fitting it, we read the black hole's mass spin and the detailed shape of the gravitational well. It's like mapping a canyon from the echoes of a whispering traveller spiralling down its walls. Taken together, these advances change our relationship with the centre of the Milky Way. Sagittarius shifts from a distant enigma to a laboratory, a place where we measure how black holes co-evolve with galaxies, how magnetic fields throttle or feed accretion, how spin remembers a lifetime of meals and mergers, and how gravity itself behaves when pushed to its limits. The first images gave our black hole a face. Gravitational waves will give it a heartbeat. Polarization will sketch its nerves and muscles, and long patient movies will teach us its habits. The rhythms by which it breathes, feeds, and occasionally flares. Whether or not Earth is here to see the grand finale of the Milky Way Andromeda Union, the path from now to then is clear. Build sharper eyes, keener ears, and smarter tools. Listen across the spectrum. coordinate messengers, follow the signals patiently. In doing so, we won't just see Sagittarius A, we'll know it in motion, in music and in light.